Is my screen visible?
Yes, it's visible.
Okay. So, good evening, everyone. Myself, Dr. Varinder Kumar, Associate Professor in the Department of Mathematics, Shahid Bhagat Singh College, University of Delhi. First of all, I would like to thank the organizers of this conference who have organized this conference so wonderfully and especially in this blended mode. So, distance is just a number now. You can go attend conferences and give talks from any part of the world. So, as Professor Sumit told you that my talk will be on kg frames and 2 kg frames in Hilbert spaces. So basically in this talk, we are going to talk about some properties and results that we have obtained in this direction. And this work has been done jointly with Ms. Sapna Malhotra, who is a research scholar with me. So first of all, I'm going to give some notations that we'll be using throughout so that you will be knowing what notations, basic notations are being used. So H will be used to denote a separable Hilbert space. BH1H2 is going to be denoting space of boundary linear operators from Hilbert spaces H1 and H2. BH is the space of all boundary linear operators on H. RT is the range of operator T, T star adjoint. Most of you might be knowing all these notations. J is a countable indexing set, and L2 Hj is the sequence space where elements of sequences are coming from Hilbert spaces Hj's. And we are taking these Hj's to be closed subspaces of the separable Hilbert space H. So this is how L2Hj is defined. So now we have some preliminaries, some basic results that we have used, some definitions that will be used in the development of this theory. So first of all, frames were introduced by Duffin and Schoffer in 1952, and they defined frames to be a sequence of vectors in H which satisfy this inequality. If only the right-hand part of this inequality holds, then this is called a Bessel sequence. If we are able to find the constants A and B such that both of them are equal, then we say this frame to be a tight frame. And if both A and B turn out to be equal to 1 and satisfy this inequality, then we call this frame to be a Parseval frame. Then the concept of G frames were introduced by W. Sun in 2006. And they defined, basically they defined generalized frames, and it is a sequence of operators from S to Hj. And they call this sequence of operators to be a generalized frame or G frame in short, if there exist constants satisfying this inequality. So inequality part is similar to that one. And again, if only the right hand inequality holds, then this sequence is called a G Bessel sequence or generalized Bessel sequence. Then Gavruta et al. Defined K frames, and they used a bounded operator H on the Hilbert space H, and they used it to study the atomic decomposition of an operator. And how they used is if K is a bounded operator on H and sequence Fj is said to be K frame for H, if we are able to find two positive finite constants satisfying this inequality. So if you notice carefully, in a frame and a K frame, the left hand part of this inequality changes, and we use the range of operator K star. So this K plays an important role in this. And again, from this inequality, third, we can easily observe that if you have a sequence which is a K frame, then right hand inequality automatically holds, and this K frame becomes a Bessel sequence. So every K frame is a Bessel sequence automatically. Then Zhu et al. Gave the notion of KG frames, which was restricted to the range of boundary linear operator K, and they basically amalgamated the concepts of K frames and generalized frames, and they gave the definition of this KG frame. So again, we are taking K to be a bounded operator on H, and this lambda J is a sequence of operators from H to Hj. Then this sequence of operators lambda J is called a KG frame if this inequality holds, we are able to find constants A and B, and constants are obviously like earlier, they are positive and finite. So if this inequality holds, then we call this frame to be a KG frame. And if I take K to be the identity operator, then this frame is nothing but a G frame, right? And every KG frame is a G Bessel sequence because right hand inequality holds automatically or trivially by the definition. Then from these, like in the concepts of frames, G frames, we can define the pre-frame operators and analysis operator and frame operator. We have not done that for earlier cases because that might have been done in the yesterday's lectures by many speakers. So we are doing it for this KG frame because we'll be dealing mainly with KG and 2 kg frames. So these operators are going to play an important role. So we might be interested in the knowledge of how these operators act. So we are going to take this bounded linear operator T lambda from L2 Hj to Hj. This is the same sequence space that we have defined earlier. So we are defining it T lambda on this sequence Xj to be summation of this lambda j star Xj. And if this sequence that we have done this is a KG frame, then this operator is always well-defined and bounded linear operator, and it is called the pre-frame operator. And it is can easily be worked out. And these are available in standard books of frames also. Then the adjoint operator of this T lambda is T lambda star, and it is defined by T lambda star of x is this sequence lambda jx, and all these elements are going to belong to Hj only. So this sequence is going to belong to L2 of Hj. And this is again turns out to be a boundary linear operator, and this operator is called analysis operator. And if I take composition of these two operators, analysis and synthesis operator, this operator S from H to H, which is defined by S lambda is T lambda star, which further gives us this. So this also turns out to be bounded linear, and this is called the frame operator for this KG frame. Okay. Then we have KG dual frames. So if you have lambda j is a KG frame and theta j is another KG frame, then theta j is called KG dual of lambda j if T lambda T theta star comes out to be identity on range of K. All right. Then we have this bounded below operators. Generally, when we talk about bounded operators, they are always taken to be bounded above. So we are going to consider this bounded below property also. So an operator K is said to be a bounded below operator if there exists constant C such that norm of Kx is always greater than equal to the Cx. And then we have this resolution of identity operator that also might be familiar to all. A family of bounded operators gamma j on H is called resolution of identity. If whenever we have this series expansion of X, where this series gamma j x converges unconditionally for all X belonging to H. Then these two theorems will be used in the results. So I will quickly mention them. This is Douglas factorization theorem. And second one is about the construction of new KG frames. And it is about if lambda j is a G frame, then lambda j k star is a KG frame with respect to Hj, and it has been proved by in this reference. So now we come to main results. So first two results are trivial, so I'll just skip them and I'll move to this one. And in this theorem, we have talked about basically the algebra of KG frames. So if we have a sequence of operators lambda j, which is both K1 and K2 G frame. This is a KG frame with respect to two operators, bounded operators. And then the following holds. Then lambda j is also a alpha K1 G frame and alpha K2 G frame for constant alpha, which is non-zero with respect to Hj. Then this is also a K1 plus K2 G frame, and lambda j is also a K1 K2 G frame. So all these results hold. So linear combinations of these operators will again turn out to be a KG frame. And I have just given main points of the proof, 2-3 lines. I have skipped the calculations part from that. So anyone interested can go through it. So these basically use the definitions and some inequalities and some basic properties. So next I'll move to this result. So Hua and Huang proved that for K belonging to BH, which is a bounded operator on H, if lambda j is a G frame, then lambda j K star is a KG frame for H with respect to Hj. So let K is a bounded below and lambda j be a such that lambda j K inverse is a G frame for Rk. Then lambda j K star is a Kg frame for H with respect to Hj. So we have used this result to prove our this theorem 6. And this is the outline of this proof. Next, we have observed that a Kg frame for a Hilbert space need not always be a G frame. It's not essentially a G frame. Kg frame need not be a G frame, and it has been uh, proved with the help of this example. We have provided this example to show that every Kg frame need not be a G frame. And we have taken Hilbert space to be R4, and Ej is an orthogonal basis for H, and we are taking one-dimensional subspaces of H. Hj is span of Ej. And if I define my operator K from H to H by this, and I define operators lambda j's from H to Hj by this, then we can show that this lambda j is a Kg frame for H with respect to Hj, but it's not a G frame. As for if I take X to be even, then this sum turns out to be 0. So lower inequality is not going to hold for any case because this should be greater than equal to A times norm X square. So it is not a G frame, but it will always be a Kg frame because K star X is going to satisfy that inequality. So we have given an example to prove that a Kg frame for Hilbert space need not essentially be a G frame. So then it was natural to ask for condition on the operator K under which Kg frame will become a G frame in all these circumstances. What are the conditions on this operator K? So if I take K to be a bounded operator on H such that K star is bounded below, and this sequence lambda j is a sequence of operators from S to Hj, then and this is a Kg frame, then this will always turn out to be a G frame. So we have tried some conditions on that also, but this condition was sufficient to prove that lambda j is always a G frame if lambda j is a Kg frame. Now we may also try to ask what are the conditions on operator K such that a G frame will become a Kg frame. And in this regard, we have this result that if lambda j is a G frame with respect to Hj with bounds A and B respectively, then lambda j will always be a Kg frame if I might take my operator K to be S lambda, the frame operator. So with the help of that frame operator, it will always be a Kg frame if I take K to be S lambda. And this is what we have, how we have proved this result. Then we try to work out what happens to the sum of two Kg frames. And in this direction, we have seen that sum of two Kg frames need not always be a Kg frame. And we have this result. This is the same example. If I take K is an operator, this is the same operator that we have taken, and lambda j's are same as we have done in the last example. And if I take the sequence gamma j to be minus of lambda j, I take negative of all of them, the sum will turn out to be 0. Then their sum will be 0 because of my choice, and this will always be 0, and therefore this is not a Kg frame because the lower condition, lower inequality will not be satisfied. So we can check that both of them are Kg frames, but their sum is not coming out to be Kg frame. So then again we started working in this direction. What are the conditions on operator K or the elements so that their sum will also turn out to be kg frame. So first we have proved that find the condition under which a sum of kg frame and a G Bessel sequence will be a kg frame. And then our main question will turn out to be corollary of this result. So first we are going to find a condition under which sum of kg frame and G Bessel sequence will be a kg frame. So k is the same bounded operator, lambda j is a kg frame, and I have taken gamma j to be a G Bessel sequence. And pre-frame operator of this is T gamma. So if we are able to find a positive constant beta such that A is greater than equal to 2 beta and norm of T gamma star x is less than equal to beta times norm k star x whole square, then this sum will be a kg frame with respect to H. And this is how we have proved this result. So G Bessel sequences sum is also always a G Bessel sequence. Therefore, this is a G Bessel sequence. And this is what these conditions and the conditions that we have taken as hypothesis are going to work it out. The sum is coming out to be a kg frame. So the main result that we started chasing in the beginning, that when the sum of two kg frames will again be a kg frame, becomes a corollary to this previous result. So if lambda j is a kg frame and gamma j is also a kg frame, and their bounds a1, b1, a2, b2 are given to us. And if I take a to be minimum of a1, a2, b to be maximum of b1, b2, and t gamma is a pre-frame operator for gamma j, satisfying the same condition, and beta is a positive constant satisfying the same condition, then this sum is a kg frame. So this becomes a direct corollary to our previous result. And then we have found a relationship between kg dual of sum and sum of their duals. So if we are taking two kg frames, lambda j and gamma j, with respect to hj, such that their sum is also a kg frame. And if theta j and psi j be kg dual frames of lambda j and gamma j with pre-frame
Professor
operators t
Virender,
theta and t psi.
Professor Virender, you have only 2 minutes more.
Okay. So if we have this theta j and psi j to be the kg dual frames of lambda j and gamma j, and if this inequality holds, where beta is a positive constant satisfying the again previous condition, then half times theta j plus half times gamma j is kg dual of lambda j plus gamma j. So basically in this result, we have found a relationship between sum of dual and dual of sums. See, in the first part, we can see that we are talking about half of sum of duals, G duals of this kg frames, and this is kg dual of this sum. So this is a very important result, which gives us this relationship between sum of duals and dual of sums. And then we have defined 2 kg frames. So I'll directly move to 2 kg frames. So basically, this is more general result than previous one, because last time we have just talked about the sum of two kg frames. Now we are talking in a sense a linear combination of kg frames. If lambda j and gamma j are frames, and we are taking their combination with the help of operators u and v, where u and v are operators which are satisfying these conditions. U is commuting with k star, and norm of u star x is greater than equal to x, then this linear combination is turning out again to be a kg frame. So this is theorem 15 is more generalized version of the previous one. And then while working on these kg frames, it was observed that if bounded linear operator k star is injective and has a close range, then for this kg frame lambda j, this inequality holds. And this motivated us because here we are getting k star on both the sides. So we defined two kg frames because one kg frame was having k star on the left side only, not on the right side. So we are able to find k star on the right side also, then we are going to call it 2 kg frames. And this is how we have defined 2 kg frames. If this inequality is replaced by this one, so it will be called 2 kg frames. And the rest of the part, we have discussed some properties of 2 kg frames. For example, every 2 kg frame is a kg frame, but converse is not true. Example has been provided. And then we have worked out some conditions when it will happen and what will happen to some other things. So if the moderator allows me, then I can continue further with one or two results.
Go ahead, take 2 more minutes.
Okay, thank you very much. So next, after 2 kg frames, now I'm just going to tell you one or two important results, and then I'm just going to wind up. So if K star is bounded below, then every kg frame will be a 2 kg frame. So this was trivial, so I'm just going to skip it. Again, sum of kg frame and 2 kg frame need not be a kg frame. An example has been provided, and it required a lot of discussions to prove this. So we look for conditions under which sum of a kg frame and 2 kg frame will again be a kg frame.
एक हफ्ते प्यार से बोल रहे मतलब मैं आज मार रहा हूँ आपको मैं आप कहते हो प्यार से बोलो प्यार से बोलो बोलते प्यार से बोलो
Please off your mic. Anyone out there, please off your mic first. Let only speaker open his mic.
Shall I continue?
Go ahead.
So I'll wind this presentation with this result, which relates the resolution of identity operator and 2 kg frames. So as defined in my preliminaries, we have defined resolution of identity operator. And if K is a bounded operator in H and lambda J is a G Bessel sequence with Bessel bound B, such that this lambda J star lambda J is a resolution of identity operator on H, then lambda J K star is 2 kg frame for H. So this result tells us that when will a G Bessel sequence will become a 2 kg frame if this operator lambda J star lambda J becomes a resolution of identity operator, and this is how the proof has gone. So finally, I would just like to conclude with by showing some selected references for my work. Yeah. Thank you very much, everyone, for your patient listening.
Thank you, Professor Virendra Kumar, for the interesting talk that you have delivered. Any questions? Okay. So, Professor Virendra, I just have a query.
Yeah, please.
Is the condition that you have taken in the definition of kg frames that the operator K should be a bounded operator? But in between, you define the concept of bounded below operators. Is the condition of bounded operator can be replaced by a bounded below operator only in the definition?
No, bounded above operators are always used, and in standard textbooks that we have seen or encountered, every time we have seen a bounded operator, the bounded above condition has been taken, and never has been mentioned that it is bounded below also. So that's why that we have chosen this, that the operator should be bounded below, because we are using that condition to prove our results.
But in the definition of kg frames, bounded above condition of an operator will automatically satisfy. So I think bounded below operator will work in the definition.
No, bounded above condition is also needed. When we are saying that bounded below, we are just taking the lower bound, not the upper one. So bounded operators, definition of bounded BH, that K is belonging to BH, the upper bound is also needed, and that we have used. Yeah.
Thank you, Professor Virendra, for your talk.
So shall I stop my presentation?
Yes.
Thank you.
Okay. So the second talk in this session would be by Professor Leena Kathuria, and the title of her talk would be Approximation Using Bias Transformation of Wavelets. Is Leena
Good
is
morning, sir. Yes, sir. I'm sharing my screen.
there? Please go ahead.
Is my presentation visible?
Yeah, it's visible. And further, I request everyone out there, please check up your mics. Only the speaker mic should be open, and rest please close your mics. Go ahead, Leena.
Okay, sir. Just a minute. Okay. First of all, a very good morning to all of you, and I would like to thank the organizers for providing me this opportunity to present a talk on the topic approximations using Bose transform of wavelets. This work has been done in joint coordination with Dr. Shashank Goyal, Dr. Nikhil Khanna, and Dr. S.K. Kaushik. So I'll go ahead, and in this talk, basically, we'll cover first of all the sufficient conditions that are required to approximate functions lying in the class L2R. That means the square integrable functions using Gauss transform of wavelets. We'll use Holder continuity of a function to reduce the wavelet coefficients. We'll discuss the relationship between Bose transform of wavelets and modulus of continuity of a function. And we'll study also the uniform approximation of wavelet coefficients of square integrable function. So first of all, I'll like to discuss the motivation behind our work. The motivation behind our work was by Dr. Nikhil Khanna, Dr. Kumar, and Dr. S.K. Kaushik in their esteemed work that approximations of functions using Hilbert transform of wavelets. In their work, they analyzed vanishing moments of Hilbert transform of wavelets and reduced various results to approximate square integrable functions using the Hilbert transform of wavelets. So this is a result in the form of theorem 1, which was given by Khanna et al. And they attained sufficient conditions for higher order vanishing moments of Bose transform of wavelets. So first of all, we assumed a wavelet which was belonging to L1R, that means which was integrable, and further its first derivative and Fourier transform was also integrable, and we took conditions that such that for some n belonging to natural numbers, x to the power n minus 1 into xi of x, eta to the power n into xi Fourier transform of eta should be integrable. Further, x to the power n into xi of x should be square integrable, and integral of x to the power q into capital G of x dx is equal to 0 for some q lying between 0 to n, where g of x is integral from -1 to 1 of this whole function provided here. So if psi j k is an orthonormal system on R, then the integral of x to the power q into Bose transform of psi x dx is equal to 0 for some q lying between 0 to n. They also prove that wavelet coefficients of a square integrable function decay rapidly as j tends to infinity depending on number of vanishing moments and smoothness of S. So this is the result that they also gave, which is stated in the form of theorem 2. Now we have generalized this theorem 2 in using Bose transform of wavelets, and we have stated this in form of theorem 3, where we took a function f which was both square integrable and it was p times differentiable, such that its pth derivative was belonging to L infinity R. That means it was bounded. So if we assume our xi to be a wavelet with compact support such that it satisfies the four conditions listed here, where gx is the function integral from -1 to 1 of this function, then there exists a constant m which is positive depending on p and fx, such that the such that the inner product of mod of inner product of f with the Bose transform of psi j k is less than equal to m into 2 to the power minus j into p plus half for every integer j and k. And this capital B psi j k is denoting the Bose transform of the wavelet psi j k, which is given here. So next we'll discuss the results relating to regularity. So what is basically regularity? Regularity is used to describe the smoothness of the function. By the smoothness means we'll have the continuous derivatives of a function up to some definite order in the domain, and the greater regularity will imply the more smoothness of the function. So regularity of a wavelet base often influences the stability of wavelet coefficients reconstruction, with a specific regularity of wavelet being required to obtain a better reconstruction signal. Further, the Holder spaces also permit to designate a notion of smoothness or regularity of a function known as Holder exponents. So, in this, or using all these properties, Khanna et al. Give sufficient conditions to decrease the wavelet coefficients by employing uniform Holder continuity. The result is given in the form of Theorem 4, which states that if f is a square integrable function, which is n times continuously differentiable function such that its nth derivative is Holder continuous with exponent beta lying between 0 to 1 and xi being a square integrable function, we a wavelet, which satisfies these two conditions. Then the mod of the inner product of f with the Hilbert transform of xjk is less than equal to this value. So we have generalized this theorem 4 in terms of Bose transform of wavelets, and this is the result theorem 5, which states that if f is a p times continuously differentiable function and its pth derivative is Holder continuous, then and if it satisfies the following three conditions, then the mod of the inner product of f with Bose transform of psi jk is less than this constant. Next, the property of modulus of continuity is being used, which is again used to describe the smoothness of the function. The result is here in the form of theorem 6, where we have provided a sufficient condition for uniform approximation of wavelet coefficients of function of square integrable function using modulus of continuity. So we have taken an integrable wavelet such that its Fourier transform is also integrable and its Fourier transform vanishes at 0. Then, and if Bose transform of wavelet psi is of compact support and its norm over L1 is also bounded, and norm mod of Gx is again less than infinity, that means it's bounded, then this norm of inner product of f with Bose transform of xi jk over L infinity will be equal to this right side. Now we present a sufficient condition for uniform approximation of wavelet coefficients of square integrable function with bounded pth derivative and prove that it decays quickly as j tends to infinity. So this is the theorem in form of theorem 7, where we have taken a wavelet psi, which is again integrable. Its first derivative is also integrable and its Fourier transform is also integrable. And if it satisfies these following conditions, then we have that the norm of the inner product of f with Bose transform of psi over L infinity will be equal to this constant. So basically, in this talk, we have approximated functions belonging to the class L2R using Bose transform of wavelets. We have studied some important properties. We have used these important properties to approximate or to estimate these functions and to reduce the wavelet coefficients. We have used properties like Holder continuity and modulus of continuity to derive those results. And these are the references that I have used and yes, these are my references that I have used. So thank you very much for providing me this opportunity.
Thank you, Professor Lina, for this talk.
Thank you, sir.
I request if there is any query and doubt regarding the talk, please go ahead. Okay, so Professor Lina, I have some queries.
Yes, sir.
You had just in between talk about the modulus of continuity of a function.
Yes, sir.
Is there any relationship between the differentiability of the function and the modulus of continuity? I just want to know, just for out of the curiosity.
relationship between differentiability and modulus of continuity. Right now I cannot recall,
Or can you
but I'll
give me
definitely
more?
check and
No, it's just out of a curiosity, nothing much.
if your
And
question is very good, but right now I cannot recall. I'll definitely tell you.
can you give me some motivation to study this bias transform?
Yes, actually, the motivation behind Boost transform was that it was used to study those functions whose Fourier transform vanished or a particular interval like -1 to 1. Close,
Okay.
so this transform was basically introduced to study those functions whose Fourier transform was vanishing on the interval -1 to 1, or some particular interval like -k to k, where k is some integer, you can say. So those type of functions we can study using this transform.
Okay. Thank you very much.
Thank you, sir.
Okay. So we have few minutes to start up the next talk. So next talk is from Professor Anu Kapoor, and she will be talking on a review on frame representation for groups. So she is there. Is Professor Anu Kapoor is here?
You, yeah, yeah, I'm here.
But you have
I'm
few
here.
minutes more to start up your talk. So shall we wait or continue with the talk?
As you say, as you say.
Okay,
I
okay,
can
let's
start.
okay, you start and you start take 2 more minutes and then start up your talk.
Okay. I hope the screen is visible.
Yes, ma'am, it's visible.
Okay. Can I start? Or should I wait for 2-3 minutes?
You wait for 2-3 minutes and then we will start. You start at 8:40.
Okay, okay. No worries.
Ma'am, you please start.
Okay, thank you. Thank you for giving me an opportunity. Thank you, Professor Sumit. Greetings to everyone, as we are all in different time zones. I'm Anu Kapoor from India, working as Associate Professor in PGDAV College, College of Delhi University, and presently a PhD scholar at Banasthali Vidyapeeth. I sincerely thank the organizers for giving me an opportunity to be a part of this conference. Till now, it's been an enriching experience, and I've learned a lot through the conference. I would also like to express my gratitude towards my mentors, Professor Shiv Kaushik, who is also in the organizing committee, and Professor Sumit for their guidance throughout. And as the topic says, I will be giving an overview on frame representation for groups. It's a very basic presentation and might motivate few of us to come and study and go ahead with this frame representation for groups. Why is it not moving? Can I share it again? It is not going ahead.
Yes, you do it, please.
I'll do it again. It's coming here only, but it is not. Give me a moment, please. It's coming again here, but it is not. I'll have to, I think, leave and join again.
No, you just check your laptop keys.
Now it is
Now it's
coming.
working.
Yeah. Yeah, it's fine now. So this is the outline of the presentation. We'll be talking about frames for Hilbert spaces, frame vectors, group representation, and frame representation. Now, as we all know, it was first introduced by Duffin and Schoffer in the year 1942 and was not studied much later. It was only in 1980s that Dobschiss, Grossman, and Meyer again came forward with the idea of frames and observed that frames can be used to find series expansions of functions in L2R. Again, it was R. Young in the year 2000 who wrote about frames in his book, An Introduction to Non-Harmonic Fourier Series. By this time, researchers started realizing the importance and potential of frames. Also, frame theory became a subject of interest when wavelet theory began to surge in popularity. Frame analysis generated much interest in both theoretical and applied mathematics. Over the past decade, representation of signals using frames was advantageous over the basis expansions and driven by applications. It recently grown very rapidly and frames have become one of the basic tools in signal representation and processing. What is the advantage of frames over the basis? Now, basis, as we know, gives us a unique representation of every vector in the Hilbert space or in the vector space. But frames give us the liberty to choose the expansion because it is not a basis. It need not be a basis. In fact, it is a spanning set. So we can span a given vector in many ways. And we can choose the expansion as per our requirement. So that this way, frames are useful over the bases and bases have their own limitations. Now, the formal definition of frames has been discussed many times in the conference, and we know what the frame inequality is, and we know A and B are called the frame bounds, and it is a tight frame if A is equal to B, and partial if A is equal to B is equal to 1. This is also called normalized tight frame. And if only the right side of the inequality holds, we call it a Bessel sequence. And we all know the example of the Parseval frame means the frames do exist because orthonormal bases form a Parseval frame. So now we move on to few definitions and we try to generate frames through a fixed vector. One thing is we have the frames. Now we are trying to generate the frame through fixed vectors. And the first in line is the complete wandering vector. What is a complete wandering vector? A vector x belonging to H is called a complete wandering vector if capital Ux, which comprises of unitary operator is U acting on X for all U belonging to U, where it is a subset of BH comprising of unitary operator. This is a unitary group including it contains identity also. And this forms if this set forms an orthonormal basis for H, we call it a complete wandering vector. And then the normalized tight frame vector. Similarly, if vector x belonging to H is called a normalized tight frame vector for a unitary system U, if Ux forms a tight frame for span of Ux, closure of span of Ux, and it is called complete normalized tight frame vector if Ux form a normalized tight frame for H. Normalized tight frame, or again, it is a partial frame. Now, after this, what is a representation? We all know the group representation. Pi, a mapping from G to GLH, is called a representation of G if it is a group homomorphism, that is pi G1, G2 is pi G1 into pi G2, where G1, G2 belongs to G, such that for every U belonging to H, the map G going to pi GU is continuous. And it is further called unitary representation if pi G is a unitary operator on H for every G belonging to G. When we will be talking about the representation on Hilbert spaces, frame representations, we will be dealing only with the unitary representations. Now, next sub-representation, as the name says, it has to be something related to smaller than the representation. Here we will take a subspace M of H such that pi gx of M is contained in M, that is pi gx belongs to M for all x belonging to M. Then G going to pi G, which is a representation, is called a sub-representation of pi. Now, representation of groups was used to give a linear structure to G. But now in frame theory, through these representation, we will try to generate frames through elements of groups. So we'll be reversing the rule. Here we are giving G a linear structure. Now, through the group elements, we will try generating the frames for the Hilbert space H. And now next comes the frame representation. So the concept of frame representation for groups was introduced and studied by Hahn and Larson in their work Frames, Bases and Group Representation in the year 2000. And much needs to be done in this. This area, I feel, has not been explored much. Now, what is a frame representation? If G is a discrete group and H a separable Hilbert space, a representation, in this case, it will be a unitary representation. Pi GH is called a frame representation if pi G has a complete normalized frame vector. What do we mean by this? There exists some x belonging to H such that pi Gx G belonging to G forms a normalized tight frame for H. So we can see x is fixed. This is a fixed vector and is generating a frame through the elements of G. And this we can see that if I take a left regular representation, then we can generate the orthonormal basis for L to G, where G is a discrete group, through the identity element of the Hilbert space H. So such frame vectors do exist. Now, similarly, as we've defined equivalent frames, we define equivalent frame vectors. Two complete normalized frame vectors, x1 and x2, are said to be equivalent if the corresponding frames are equivalent, or equivalently, there exists a unitary operator u belonging to pi g such that ux1 is equal to x2. Now, the two definitions are just the same. As we know, the frames are equivalent if there exists a unitary operator from the Hilbert space H to Hilbert space K, such that u of pi gx1 is equal to pi gx2. Now, since pi is a group homomorphism, so pi u of pi ex1 will be equal to pi ex2, and pi e will match onto the identity operator on H. So we'll get ux1 is equal to x2. And then next we define the equivalent frame representations. The two frame representations pi gh and pi dash gk are said to be equivalent if there is a unitary operator w from h to k such that w pi g adjoint of w is equal to pi dash g, where for all g belonging to g. It is in sync with all the definitions of the representations. Now, next comes, after defining this, next comes the important result, which connects the equivalent frame representations and frame vectors. And we have the theorem that, or the result, which is simple to prove, that let pi gh and pi dash gk be two frame representations. Suppose that x1 and x2 are two complete normalized type frame vectors for pi and pi dash respectively, such that pi gx1 and pi gx2 G belonging to G are unitarily equivalent as frames, where G is just the index set, then pi and pi dash are also unitarily equivalent. That means if the frames are equivalent, then the representations are also equivalent. Now, we know, as far as frames are concerned, that every normalized tight frame can be extended to a orthonormal basis, and every other base frame can be extended to a Ries basis. On the same line, suppose U is a unitary group on H and X belongs to H is a complete normalized tight frame vector for U, then there exists a Hilbert space K containing H and a unitary group G on K such that G has a complete wandering vector. Now, complete wandering vector means corresponding frame is an orthonormal basis, and H is an invariant subspace of K such that G restricted to H is nothing but U, and the map G going to G restricted to H is a group isomorphism from G onto U. Now, this can be used here to prove that every frame representation of G is unitarily equivalent to a sub-representation of the left regular representation. Here, what we do, in the previous proof also, we always define K to be L to G, and here also, where G is given to be a discrete group, we will take K to be L to G and lambda, the left regular representation of G, and M, the von Neumann algebra generated by lambda G, G belonging to G. And if P belongs to commutant M, then we define the sub-representation lambda P G going to lambda G E for all G belonging to G. This defines a sub-representation because lambda GP is contained in M. Using this and the previous result, we have that every frame representation of G is unitarily equivalent to a sub-representation of the left regular representation. That means we can limit ourselves to studying left regular representation, as every frame representation is unitarily equivalent to left regular representation. Now, next thing in the sequence is the frame multiplicity. What is frame multiplicity? It is this in natural number n, the supremum of all natural numbers k, with the property that there exist frame vectors xi such that pi g xi, G belonging to G, are strongly disjoint. Strongly disjoint means each of them separately is a normalized tight frame, and jointly they form a normalized tight frame for H direct sum H direct sum H. Here it does not mean direct sum, it is just n copies of H. Now, the next theorem gives us the condition for existence of complete normalized tight frame vector for pi n G Hn, where pi n is direct sum of pi and Hn is direct sum of H. See, pi gh always have a frame vector. Why? Because that is the definition of the representation. So this theorem gives us when will pi n G Hn have a complete normalized tight frame vector. And this says it will have a complete normalized tight frame vector if and only if there exist self-adjoint projections Pi in M dash, which is commutant of M, such that Pi is similar to P and Pik is orthogonal to Pjk when I is not equal to J, where K is equal to L to J. So this has given us the condition when the direct sum will have the complete normalized tight frame vector. Next, we talk about, and using this, we can prove that frame multiplicity of the frame representation is always finite. That means, what does that mean? That means there are only finite disjoint classes of the frame vectors. Like frame vector will, the equivalent frame vectors will fall into the same equivalent class, and multiplicity of pi is finite means the disjoint equivalence classes of the frame vectors will also be finite. The next is, when does the frame representation has multiplicity 1? Now, what do we mean by multiplicity 1? Multiplicity 1 means there is only practically a one class of generators, one class of frame vectors. That is, first, if P belongs to M intersection with M dash, which is equivalent to saying that M belongs to center of M. If G is an abelian group, then also every representation of G will have the multiplicity 1. Now, suppose that pi GH is a frame representation. Complete normalized tight frame vector X is also a trace vector for the von Neumann algebra pi G. Then also pi has a frame multiplicity 1. So there are cases when frame multiplicity is 1 or the basic frame vector is just 1. And so the class is also simple. Now, next is the final result which we arrive at. And that is the important, which sums up that we can literally count the all complete normalized frame vectors. What does it state? It says if X is a normalized tight frame vector for pi GH, then set of all complete normalized tight frame vectors for pi G is nothing but equal to the set UX, where U belongs to U of W star pi G, that is
I request everyone, please off your mic. Only speaker is allowed to open his or her mic. Please. Ma'am, please go ahead.
Thank you. The final results let us know that it tells us about the complete set or the whole set of all complete normalized tight frame vectors for the representation pi. And it is equal to Ux, where U is the unitary operator on the von Neumann algebra generated by pi G. And so in this way, I think the group representations are important, which gives us an insight into the tight frame vectors. Thank you. And that is for all from my side on the basics of this group representation. And these are some of the references which I have gone through. Along with that, the Dunn and Larson, which is the basic, they introduced this concept of group representations. Thank you.
Thank you, ma'am, for this talk. It's quite interesting. Is there any question? Please do ask.
Yeah, I have a question. First of all, I would like to thank Professor Anu Kapoor for this very insightful talk, where she has discussed a lot of things about frame representations, group representations. I have a very general question that, is there any relationship between any two distinct wandering vectors?
Please repeat.
Is there any relationship between any two distinct wandering vectors?
They will both generate orthonormal bases. And as orthonormal bases can be many, so wandering vectors can also be many.
Okay. Thanks a lot.
Any other questions? Thank you, ma'am. Thank you for the talk.
Thank you so much. I'll stop sharing.
So the next talk in this session will be by Shankar Gulia, and he will be talking on uncertainty principle and Jack transform on finite non-abelian groups. Is Shankar is here? Professor Shankar is here?
Yes, I'm here. Can I
You please
present?
go ahead. Definitely. Please go ahead, please.
Is my screen visible?
Yes, Professor Shankar, you please go ahead.
Hi, I'm Shankar from Department of Mathematics, Janki Devi Memorial College, University of Delhi. So my talk is uncertainty principle and Jack transform on finite non-abelian group. So this is the overview of my presentation. Introduction, motivation, and then preliminaries, and then Jack transform on finite non-abelian group, then main result, and then in the last references. So in introduction, mostly signals occur in the form of time domain representation, which are either sequences or functions represented against time. If the signal is defined at all instant of time, then it is called as an analog signal or continuous time signal. If the signal is defined at discrete instants of time, then the signal is termed as a discrete signal. Signals can also be modeled in the frequency domain representation, where the variation of signals in terms of frequency is used to characterize the signal. In practical, we cannot compute exact integral and infinite series. So in this digital world, it is essential to replace continuous and infinite representation by a finite representation for the reason of computation. For instance, we replace time domain or frequency domain like real line R or integer by a finite time or frequency domain like finite ring Zn, integer modulo n. For the sake of computation, real Fourier transform is replaced by discrete Fourier transform. Discrete Fourier transform is a fundamental tool in digital signal processing with application in image processing, fast convolution, computation, or quantum computation, etc. One of the foundational problem in modern signal processing is to recover signal from the linear measurement, that is mx equal to f, where f is the signal and x is the unknown vector with n components, and m is the measurement matrix of order m cross n. The scientist Donoho coined the term compressed sensing, that is CS, in which the signal sampling technique and signal recovery technique are both covered in compressing sensing. Compressed sensing is to find exact and approximate solution for undetermined linear system of equation, which cannot be solved using traditional linear algebra techniques. The application of compressed sensing in the signal processing arise from the principle of sparse representation. The uncertainty principle of discrete Fourier transform plays a key role in development of compressed sensing. So here are the preliminaries. So first we have a definition of L square G. So L square, if we have a finite group G, then L square G is the set of all functions from G to complex number. Then we have a definition of inner product. If we have a space L square G, then inner product of two element F and H are summation F of G into conjugate of H of G, where summation running over element G from group G. We denote the order of group G by this notation. That is mode of G. Next, we have a definition of sparse norm of a element from L square G. Sparse norm of an element from L square G is the number of non-zero element in the vector F. And this is the notation, norm 0. So this is not a norm, but it plays an important role in sparse representation. Next, we have norm of zeta, where zeta comes from this direct sum of matrices spaces over complex number. So the sparse norm of zeta is equal to summation of sparse norm, zero norm of matrices, block matrices. Then we have definition of delta function, which is equal to delta x equal to 1 if the element is identity, otherwise it is 0. Next, we have general linear group over a vector space V. If we have a finite dimensional vector space, then LV denotes the set of all bounded linear operators on V, and GLV is the set of all invertible operator. Then we have definition of representation of a group G. If we have a finite group G, then a mapping phi from G to GLV is a representation if it is a homomorphism, where this V is finite dimensional vector space. And the degree of this representation phi is the dimension of vector space V. Also, this representation satisfies this condition. Phi of inverse of phi of G is equal to phi of G inverse for all G belongs to group G. We can also represent this representation by a matrix. If we have a dimension of vector space V is equal to D, and we have a standard orthonormal basis Bk of V, then phi ij from G to C can be written like this: inner product of phi G Bj Bi, where G comes from group G and Ij is in between 1 to D. So this phi Ij is called a matrix coefficient of the representation phi. Next, we have a definition of irreducible representation. If a subspace W of V is G invariant, subspace W of a V is G invariant if phi of G W belongs to that subspace W. And this is true for all W belongs to W and for all element of group G. And if a representation phi from G to GLV have only two G invariant subspaces, that is singleton 0 and V, then that representation is irreducible. Then we have a definition for unitary representation. A representation phi from G to GLV is unitary if phi G is a unitary operator for all element of group G. Then we have a definition of equivalent representation. So two representation phi and psi, where phi is from G to GLV and psi is from G to GLK, are equivalent if there exists an isomorphism between two vector space V2K that satisfy this condition. That means that isomorphism is commutative with respect to phi and psi. Next, we have a Fourier transform on finite non-abelian group. So we define Fourier transform on finite non-abelian group. if we have a group of order n, if we have a finite group of order n, then the set of inequivalence irreducible unitary representation of G, that is pi 1, pi 2, these are the notations of representations, and dk is the degree of all irreducible representation, pi k. If we take qk is equal to square root of dk, that is degree of irreducible representation, divided by n, then we define a function f of k on group G from L square G to set of space of matrices, which is equal to summation fx into this qk into conjugate of this irreducible representation pi k, where summation running over element of G. So using this function fk, we can define Fourier transform on L square G. So the Fourier transform is a mapping from L square G to direct sum of matrices space over L2, which is equal to this transpose of a matrix, where column vectors are F1, F2, Fs. Next, we have adjoint of this Fourier transform, that is Fg star, which is conjugate transpose of this matrix. So when we composing this Fourier transform with its adjoint, we get same element f, that is this Fourier transform is a unitary operator. Then we have some definitions that we will use to define a Jack transform. So the next definition is downsampling operator. So if we have a group of non-abelian group and B is the subgroup of G, so the downsampling operator H is a mapping from L square G to L square B, which is equal to DHFB is equal to F of HB, where F comes from L square G and B comes from subgroup B. We can also represent this downsampling operator into a matrix form using Kronecker delta function, and the order of this matrix is order of subgroup B into order of group G. Then we have upsampling operator H from L square B to L square G, and we can also represent this upsampling operator into matrix form, again by using Kronecker delta function. Then we have two definitions, regular right representation and regular left representation. So regular right representation is an operator from group G to GL L square G, which is given by Rx of F is equal to F of Sx, where S and X are the elements of group and F comes from L square G. Also, we can represent this right representation into matrix form, and it's a square matrix with order of group. Now we using these definition we define Jack basis and Jack transform. So let G be a finite non-abelian group, and A and B are the subgroups of G. And if we have a monomorphism from subgroup B to G, then G can be written as semi-direct product of HB and A. Let phi k be the set of irreducible unitary representation of subgroup B. So this collection Tk phi ijk is an orthonormal basis. This becomes an orthonormal basis for L square B, where Tk is the square root of Rk upon order of subgroup B, where Rk is the degree of irreducible representation phi k. Now we define a function theta, which is equal to right representation of A inverse into upsampling of H into Tk into irreducible representation phi ij k, where A belongs to A and k is from 1 to m and I and j in between 1 to dk. So using this function, we get a set. That set becomes an orthonormal basis for L square G. That is, theta k ij is an orthonormal basis of L square G. And this set, we can say this is a Jack basis for L square G. Now we define Jack transform. Jack transform for L square G is a map which is equal to summation of downsampling H into regular right representation R A into f of B into conjugate of representation phi k, where summation is running over element of subgroup B. So using this Jack transform, we have the following results. The first one is Jack transform of convolution of two elements f and g, which is equal to summation Jack transform of f into Jack transform of g, where summation is running over element of A. Then we have two theorems. One is for Fourier transform and second one is for Jack transform. So using Fourier transform, we have an uncertainty principle that gives us the sparse norm of f, product of sparse norm of f with Fourier transform of f strictly greater than order of g upon d1, where d1 is the maximum of dj, where dj are the degree of irreducible representations. So if we use Fourier transform, then we get this result. When we use Jack transform, then we get this result. Uncertainty principle of Jack transform. That means sparse norm of product of sparse norm of f with Jack transform of f, which is greater than order of b upon t1, where t1 is the maximum of ti and ti are the degree of irreducible representation pi k. So we can see that using Jack transform, we get the better sparse solution as compared to Fourier transform. So these are the references that I have used. Thank you.
So, thank you, Professor Shankar, for the talk. Is there any doubt or query? Please, anyone, do ask. So, Professor Shankar, I have a small query.
Yes, sir.
Is there any relationship between Jack transform and Fourier transform?
When we define Jack transform, we use a semi-direct product group. And
Okay.
if using Jack transform, we can find Jack basis using a operator. So it's very easy to represent a signal by using Jack basis as compared to
So,
Fourier basis.
so it means Zach transform is better than Fourier transform.
Yes, sir.
Always, always, or in some cases.
Yes, yes. It takes very less time to represent a signal when we use Jack basis.
Thank you, Professor Shankar. It's quite interesting talk. Thank you very much. So the next talk in this session, and this is the last talk of the session, and it will be delivered by Sandeep Kumari, and she will be talking on a note on fractional Gabor systems in L2R. Is Sandeep Kumari is here? Is Sandeep Kumari is here? We got your message, but you're not audible. So she is not able to unmute. I request the host if they can help
Yeah,
regarding unmute.
just a moment. Let me just look at her mic. I think I'm trying, but I'm not able to do it. Maybe if she can just sign out and log out and log in again, maybe she will be able to do it. So I think she has already, she already left. Yeah.
She's trying.
Yeah.
So how are you, Professor Nikhil? Is everything is fine over there?
I'm good. Yeah. Thanks for asking. Yeah. How about you?
We are also fine. So what's the
Yeah,
time over there?
It's 7:50.
We are faster than you.
Yeah, you are 1 hour 30 minutes faster than us. Yeah. Good to see you.
So, I listened your talk also. That was very nice.
Yeah, thank you very much. The feeling is mutual, actually.
Now it's so easy to connect everyone.
Yeah.
No matter in which part of world you are.
Yes.
You just try to contact Sandeep Kumari if you can.
Yeah. Give me some few minutes. I'll just contact her. Thank you. I suggest maybe if she's not able to unmute her mic, maybe we can switch over to the next speaker, and maybe by the time she may be able to rectify what are the problems.
So this is the last time of my session. Is Professor Joan is here?
I think on his behalf, Professor Alfredo Rees, maybe he can chair the session. He is available. Yes, Alfredo Rees.
Hi, Professor Alfredo. Are you there? Are you listening? Professor Rees, are you there?
Let me just try again.
Hi, hello, I'm here.
Hi, Professor. How are you?
Hi.
So my job is over. Now you have to take over this chair.
Yes, well, I
Thank you
see
very much.
here is the next speaker is Nitin Sharma. I
Yes,
don't
sir.
know if
Yes,
he
sir,
is
I'm here.
already. Yes, you are there. Yes.
Yes.
Perfect. Because we have problems with the other speakers, so we have to change to go ahead with your presentation, please.
Okay. Sir, my screen is visible.
Yes, we can see
Okay.
your slides.
Okay, thanks.
So, please go ahead.
Okay. My greetings to all. First of all, I would like to thank the organizer and chairperson of this session, Professor Alfredo, for this opportunity to present my work. The title of my talk is Woven K-frames in Quaternic Hilbert species. It is the joint work with Professor Sumit Kumar and Professor Koleti Moti. This talk is divided into 3 sections. In the first section, we have given the basic definition of frames in Hilbert spaces and frames in quaternic Hilbert spaces. And in the second section, we have given the definition of woven K-frames in quaternic Hilbert spaces. And we have studied the condition under which bounded image of woven K-frames forms of woven K-frames. And we have also studied the perturbation result on the woven K-frames. And the third section is references. Today also the importance of frames is talked by Professor Annu. Let me recall the definition of frames in Hilbert spaces. Let us consider UI be any sequence in H, any countable family of element in H. H is the separable Hilbert spaces. If there exist R1 and R2 such that if this inequality hold for every U in H, then we will say this UI, the family is a frames with upper and lower bound R2 and R1. As in yesterday talk, Professor Sumit already talked about this Bowen frames in Hilbert spaces. Distributed signal processing is the main motivation for these Bowen frames. T. Ambrose has defined Bowen frames in 2016. We have taken the N family of frames in separable in Hilbert spaces. If there exist R1 and R2 such that if for any partition of this I, if this family FP forms of frames for H with lower and upper bound R1 and R2, then we will say this family of M frames is Bowen frames for Hilbert spaces. Although this frames has many applications, but there are some problems in sampling theory which cannot be tackled by frames, which motivates Gotora to define K frames in Hilbert spaces. So let EY be the element of H and K be the bounded linear operator from H to H. If there exist R1 and R2 such that if this hold, where K star is the adjoint of K, if this inequality is hold for every U in H, then we will say this family UI forms of K frames. And if we consider the M family of K frames, if for any if there exists R1 or R2 such that if for any partition sigma j of phi, if this family phi ij forms K frames with lower and upper bound R1 and R2, then we will say this family of M frames forms of Bowen K frames. Yesterday, the field of quaternions is defined by Professor Sumit, and the motivation is also given there. So let me recall the frames in quaternic Hilbert spaces. We have taken the as quaternic are non-commutative in nature. We have taken the right quaternic Hilbert spaces, and we have taken the UI be the countable family in right quaternic Hilbert spaces. This is said to be a frame if there exists R1 and R2 such that this inequality hold for every U in HR. HR is the right quaternic Hilbert spaces. Then we will say this UI families, the countable families forms of frames for right quaternic Hilbert spaces. And this is the definition of Bowen frames in quaternic Hilbert spaces. QHS means quaternic Hilbert spaces. We have taken the M family of frames in right quaternic Hilbert spaces. It is said to be a Bowen frames if there exist R1 and R2 such that for any partition P sigma j of I, if this family FP forms a frame for every partition with lower and upper bound R1 and R2, then it is said to be a Bowen frames in right quaternic Hilbert spaces. And recently in 4, the author have defined and studied the K-frames in quaternic Hilbert spaces. We have taken the countable family of K-frames in right quaternic Hilbert spaces if there exist R1 and R2 such that if this inequality hold for every U in HR, then we will say this family forms of K-frames. This is the second section of our talk. Bowen K-frames in quaternic Hilbert spaces. In the first section, we have defined the Bowen K-frames in quaternic Hilbert spaces. Again, we have taken the M family of K-frames. And this is said to be a Bowen K-frame if there exists R1 and R2, such that if we take any partition sigma j of I, this family Uij, where I belongs to sigma j and j belongs to M, forms a K-frame with lower and upper bound R1 and R2. This is the example we have given for the Bowen K-frames, and it is not a, and this families. Okay. Let HR be the three-dimensional right quaternic Hilbert spaces with orthonormal basis E1 and E2 and E3. And we have defined K operator on HR as K of E1 equals to E1 and K of E2 equals to E1 and K of E3 equals to E2. Then the adjoint operator corresponding to K is this. Then the family UI, E1, E2, E1, E1, E2, and VI, E1, E2, E2. This family will form a K-frame, one K-frames. But this family does not form a K-frames. This family given by UI and VI, they do not form a K-frame. They do not form a frame, but they form a Bowen K-frames. And this is the second section, Bowen K-frames in quaternic Hilbert spaces. In this section, we mainly talk about the condition under which bounded image of Bowen frames or Bowen K-frames forms of Bowen K-frames. This is the first result in which we have talked about the under which condition bounded image of Bowen K-frames will form a Bowen K-frames. So we have taken the two Bowen K-frames in HR, right quaternic Hilbert spaces, and we have taken T to be an invertible right linear operator with bounded inverse, and it also commute with K. Then the TFUI and TFUI dash, this forms of Bowen K-frames for HR. In the next result, we have proved that every Bowen forms of Bowen K-frames, but converse is not true. Okay? We have taken the family of Bowen frames. Then we have, and then for any bounded linear operator, we have proved that the bounded image of this Bowen frames forms of Bowen K-frames, but the converse may not be true. That is, if a frames under a bounded linear operator forms of Bowen frames, we cannot say it forms a Bowen frames also, and this is the example. We have taken the HR to be the three-dimensional right quaternic Hilbert spaces with orthonormal basis E1 and E2, E3, and we have defined phi equals to this family and psi equals to this family. This family under the operator, this operator K, which we have defined by K of E1 equals to E1, K of E2 equals to 0, and K of E3 equals to 0, and its adjoint is K star E1 equals to E1 and K star E2 equals to 0 and K star E3 equals to 0. Then we have proved this family phi and psi under This K will form a Bowen K frames, but it does not form a, this family does not form a Bowen frames, because if we take the partition sigma equals to 1 to 3 and u equals to E3, the lower bound condition will not hold. In the next result, we have obtained a Bowen K frames from a K1 K frames. So we have taken EY to be a K frames with bound R1 and R2, and we have taken T to be any invertible right linear operator, and the inverse is bounded right linear operator, and this operator T commute with K. If norm of I minus T is less than R1 upon my R2, then this family UI and the image of this UI under T forms a Bowen K frame. This is the second section. In this section, we mainly talk about the perturbation of Bowen K frames. This is the first theorem. Let T and K be the bounded right linear operator and K has closed range. If there exists alpha 1, alpha 2, alpha 3 lying between 0 and 1, we satisfy this inequality. Then if UI and TI are the K frames in RK, then they will form some Bowen T K frames also. And this is the another result in which we have talked about the perturbation. We have taken UI to be the K frames with bound R1 and R2, and PI to be the Q frames with bound R1 and R2. And this T1 and T2 to be the surjective right linear operator which commute with K, and RK is closed. And if there exists alpha, beta, gamma, we satisfy this. Then the image of this K frame UI under T1 and the image of Q frame under T2, they will form a Bowen K frame with universal bound this and this. And this form of Bowen K frames, they will form a K frame also, as we have talked about earlier in the result. Every Bowen frames forms a Bowen K frames under the any bounded linear operator K. And these are the some selected references. Thank you, everyone.
Thanks, Professor. Is there any question for the speaker? Any comments? No questions? Well, thanks for your presentation, Professor. So
Thank you.
if there is no any comment, we are going to continue with the session, and we are going to go back with the sessions in order to let the last presentation. We have some technical problems, but we are going to try to continue with the presentation for Kumari. So I don't know, Professor Nikhil, if you can share their slides.
Hello, sir. Now I'm ready to share.
Okay, perfect.
Able to unmute and ready to share. I will share it with on my phone.
Okay,
Just
go ahead, please. Well, we can see you.
Share.
Yes, Alfredo, just give me 2 minutes. I'm going to share the slides.
Okay, we can wait. No problem. There is always technical problems with this online seminars. It's normal. Perfect. We can
Yes,
see
sir. Thank you
the
so much.
presentation.
Yeah.
Okay,
So,
so are you
hello
ready?
all. My name is Sandeep Kumari, and I'm research
Perfect.
scholar of K.R. Mangalam University, Gurgaon, from India. And today's my topic of the speech is a note on fractional Gabor systems in L2R. So please next slide. And it is my abstract. In this article, these fractional Gabor frames in L2R, these are introduced and studied. Also, a finite linear combination of fractional Gabor frame for L2R is discussed. Next, it is proved that under certain conditions, a finite linear combination of fractional Gabor frames is a frame for L2R, and then finally stability results for fractional Gabor frames are proved. And next is my introduction part, that what is the Gabor system and what is the fractional Gabor frame. So the system such as EK and this L5 with K and L are integers. These are generated by modulations and translations, or translation of a single function phi in L2R. These are called Gabor system. These are made with the help of modulation and translation of a single function phi, which is defined in L2R system. Deffen and Schoffer initiated this study of frame for separable Hilbert space. And then Debachis and all, they reintroduced the frame in L2R. And wavelet and Gabor frame is a powerful and important tool for analyzing time frequency analysis, and it has applications in various fields, including signal and image processing, sampling theory, integral equation, and many more things. And the researchers investigated additional integral transforms to study various signals, namely fractional Fourier transform, we note it as FFT, and then fractional wavelet transform FWT, then the short time fractional Fourier transform, Radon-Wigner transform RWT, and the right transform RT. FFT has many advantages but has one limitation. On the other hand, STFFT has nullified most of the shortcomings. Still, in some cases, STFFT is workable in real signals with high spectral components for short duration and low spectral components for long durations. So next slide, please. This is introduction continued, where Mendlovic and all was first to study the FWT in the light of time frequency analysis. The idea behind this transform is deriving the fractional spectrum of the signal by using the FFT. And for literature related to FWT and their applications, sir, here it is a mistake from, I just noted that in these square braces I have to put the bibliography number, and but it is a mistake from my side that I'm not able to put because the question marks are coming, and I'm really very sorry, because in my PPT these question marks are showing. So I have to do that, but I just noted this. In my final presentation, I could not put the right bibliography number or reference number here. So I'm really very sorry about that. And fractional wave packet frames was recently introduced and studied by Shah and all. For more literature FWT, I mentioned some references in last of my PPT. So sir, next slide please. So it is my introduction part, and the organization of my paper is as follow. I made 4 section. The first section was introduction part. The second section was the second section will be the fractional Geber frame in L2R are introduced, and then linear combination of fractional Geber frame for L2R is discussed. In section third, it is proved that under certain condition, the finite linear combination of fractional Geber frame is a frame again for L2R. And then in section 4, stability results for fractional Geber frame are proved. Next section. So then in the next section, here it is the first definition of the Geber system. The here let C and D be a real number, and alpha is p pi by 2, where p is any real number. Then define the fractional translation and fractional modulation operator on L2R system as defined as follow. And it is a definition of a Geber frame, that how we do the translation part and the modulation part in L2R system. And in definition 2.2, the fractional Geber frame is defined where a function phi is belongs to L2R. So the fractional Geber system is defined as follow: G alpha of phi Lk, where E alpha and Kc T alpha Ld phi, where this K and L are integer and alpha is p pi by 2, and p is any real number, where this E alpha Kc T alpha Ld of phi t is phi of t minus d E raised to power minus kct. So when we take alpha as pi by 2, so we get p is equal to 1, and then and we have E alpha kc T alpha Ld of phi t is phi of t minus d E raised to power minus E raised to power iota kct, which is a standard Geber system in L2R. So next slide, please. In definition, in the next definition, a fractional Geber system is said to be this Geber system E alpha Kc and T alpha Ld of phi, where K and L are integer and alpha is taken as p pi by 2. It is said to be a fractional Geber frame if there exists a positive number AL. There exist positive numbers AL and AU such that we take two bounds of this fraction Geber system. The lower part is AL, this norm of G raised to power 2, and the upper bound is AU G raised to power 2 for all G in L2R. So here I have given one example of fractional Geber Bessel sequence where phi is taken as chi of 0, 1, and this K and L both are taken as 1. So we can take the function as this. Next slide, please, sir. In next definition, fractional Weis-Heisenberg packet is defined, where we have taken the translation and modulation part for some function phi in L2R, and the real numbers C and D be a fractional Geber system. One may call this Hij, where I and J are integers, a fractional Weis-Heisenberg packet with respect to E alpha Kc and T alpha Ld of phi, where K and L are integer and alpha is p pi by 2. If it is of the form that Hij is sum of alpha KL and E alpha Kc T alpha LD of phi, where ij are integers, and this dij are such that union of dij, where ij are integer, are these are z cross z, and this d I dash j dash in intersection dij is phi. For I is not equal to I dash and j not equal to j dash, and alpha of k and l are any scalars. So here it is a result of fractional Gabor frame and fractional WH packets. Uh, that this system E alpha KCT alpha LD phi, where KL are integer and alpha is p pi by 2. These be any fractional Gabor frame for L2R, and Hij be fractional WH packets with respect to this taken system. Suppose supremum of Ij are integers and mode of Dij, this supremum of mode of Dij is finite, and AKL is a positively confined sequence. Then Hij is a frame for L2R if infimum of this summation AKL mod power 2 minus this summation where AKL mod into K dash L dash. This is greater than 0. This is positive. So if this infimum is positive, then this fractional Gabor frame and fraction WH packet is taken. Yes, so next slide, please. In next theorem or result, fractional Gabor frame of fractional Gabor frame and fractional WH packets, the E KCT and T alpha LD phi, where KL are integer and alpha is p pi by 2. This be a fractional Gabor frame for L2R, and Hij be fractional WH packets with respect to the system. Let T be a function for from L to Z2 up to L to Z2. This be a bounded linear operator such that this T of inner product of this alpha kc T alpha LD of phi and G, where KL are integer and alpha is p pi by 2, and if it is equal to this inner product of Hij with G, where Ij are integers for all G in L2R, then we can take then this Hij, where Ij are integer, it is a frame for L2R if and only if there exists a number k such that a positive number k such that this sum of mode of inner product of Hij and G is greater than this k times sum of square of mode of norm of square of mode of inner product of E alpha KCT alpha LD phi and G for all G in L2R. Gabor system G in L2R system. Next slide, sir. And in the next section, it is proved that under certain conditions, the finite linear combination of fractional Gabor frames is a frame for L2R. So for this, the first result is finite. First result is for finite sum for fractional Gabor frames. So let E alpha KC T alpha LD phi of I, where KL are integers and alpha is p pi by 2. This be a fractional Gabor frame for L2R, and I belongs to 1 to up to any S, any naturals, and let this alpha I, where I goes up to 1 to S, these be any scalar. Then this sum of alpha I and E alpha KCT alpha LD or and phi I, where K and L are integers and alpha is p pi by 2. It is a frame for L2R. If and only if there exists a number beta, there exists a beta, positive number beta and some R which belongs to 1 to up to S, any scalar such that this beta times of this summation is less than equal to square of norm of summation of this system, and where this G is taken from L2R system. So this is for finite sum of fractional Gabor frames. Next slide, please, sir. In the next result, fractional Gabor frame, in the next result of fractional Gabor frame, let this system E alpha Kc T alpha Ld phi I, where Kc are integers and alpha is taken as p pi by 2, and I be any scalar 1 to up to any number S, any natural S. This be a fractional Gabor frame for L2R with frame bounds AI and BI respectively. Let this alpha I, where I goes up to 1 to S, this be any positive scalars if for some R, where R is taken from any scalar 1 to up to S, we have AR alpha R AR which is greater than this sum where I is not equal to R and taken from 1 to S, and alpha I BI plus 2 times of this sum. Then this summation alpha I, where I taken from 1 to S, E alpha Kc T alpha Ld phi I, where KL are integers and alpha is p pi by 2. It will be a frame for L2R system. For the next section, stability of the fractional Gabor frames are given. So the Balan gave various stability results for Fourier frames and wavelet-Riesz bases. The Pelle-Wiener type theorems for frames in Hilbert spaces results to stability were given by O. Christine. Finally, the stability of Gabor frames is discussed and various conditions for this stability are obtained. So in this manner, this next theorem for stability of fractional Gabor frames is given, which is let this E alpha Kc T alpha Ld of phi, where KL are integer and alpha is p pi by 2. This be a fractional Gabor frame for L2R with frame bounds AL and BU and the frame operator S. Let phi dash is belongs to L2R be any function which is satisfying this condition, and this is a Bessel sequence with Bessel bound M, where this M is less than AL power 2 and second norm of S power minus 1. Then this E alpha KCT alpha LD phi dash, where KL are integers and alpha is p pi by 2, is a fractional Gabor frame for L2R system. And then finally, the stability of fractional Gabor frame is given, which is as follow. Let E alpha Kc T alpha Ld phi this be a fractional Gabor frame for L2R with bounds AL and BU, and phi dash is taken from L2R. This be any function. Then E alpha Kc T alpha Ld phi dash is a Bessel sequence in L2R system if and only if there exists a positive number k such that this result happens that sum of second mode of this inner product is less than equal to k times of this G. For L, G
Hello, please turn
belongs
off
to
your
L to R.
microphone, please, just for the speaker, please. Okay, go ahead, continue, please, Professor.
Further, if there exists a bound linear operator U from L to Z2 up to L to R, which is given as follow, such that this norm of U minus 1 raised to power 2 PU is greater than 2 times K, where K was taken as any positive number. Then this system E alpha KC T alpha LD phi dash, where K and L are integers and alpha is P pi by 2. It is a fractional Gabor frame for L2R system. These are my references and many more, and thank you.
Thanks, Professor Kumari, for your effort in this presentation with some technical problems, but we have listened to you, so thank you very much. And is there any question for the speaker?
Yes, I have
comments?
a question.
Go
Yeah.
ahead.
Yeah. Thank you. First of all, thank you for your insightful talk. I have a very general question regarding the systems you have studied in your presentations. So, I mean, what is the motivation for studying fractional frames? I mean, fractional Gabor frames.
Sir, because the main motivation is in fractional Gabor frame, mean the Gabor system where we introduce modulation and transformation together. And the fraction part is also introduced with this system. It is also new for me, but I really enjoyed this working on this and gather more and more information. So it was quite interesting for me.
Thank you very much.
Yeah, thank you, sir.
Well, thanks, Professor Kumari, again. Thank you very much. So if there is no comments, we are going to continue with the next speaker. So let me see. Here is Professor Sunderdeep. Are you ready?
Yes, sir.
Okay, perfect. So you can start sharing your screen in order to see if there is no more technical problem, please.
Okay, sir. Thank you, sir. Is my screen, sir, visible?
Yes, just if you please make it bigger.
Sundar, I think you first need to download this and then you need to open it. I mean, you are just opening it. I don't know the mode.
No, sir. I also.
You just try Control L.
Yes, sir. I am trying this Control L.
Okay. Thank you.
This is, sir, Control L not working.
Because you need to first open it. I think you are trying it using some browser.
With this plus, yes.
Yes, yeah.
Perfect. Yes, because it's not the Acrobat reader, is the web page.
Yeah.
But it's better now. So
okay. Thank you.
Professor Sunderdeep is going to talk about the analysis of orthogonal greedy algorithm in noise measurement. So go ahead, please.
Okay, thank you, sir. Hello, everyone. Myself, Sundardeep, and my talk on analysis of T-orthogonal greedy algorithm in noisy measurement. And this work is done under the joint supervision of Dr. Shiv Kumar Kaushik and Khole Timothy Pomai. Actually, in this algorithm, we extend the orthogonal greedy algorithm with the help of with the help of the Tikhonov regularization. So Basically, Donohue introduced the term compressed sensing. It is a emerging technique for signal processing and data acquisitions. It makes possible to efficient acquire and reconstruct signals using a sparse representation. Sparse means suppose we have a signal in column vector, then the sparse means that it has only few non-zero entry in column vectors. The reconstruction of signal can be observed by the following linear system. Ax equals to f. This system is underdetermined, where A is measurement matrix and x is unknown signal, and f is the measurement vector, where f diamond is the error-free exact signal associated with f, and n is the noise in the signal f. There are prime methods for reconstructing the signals are optimizations and greedy algorithms. The basis pursuit use optimization approach, whereas matching pursuit and orthogonal matching pursuit, or sometimes called as orthogonal greedy algorithm, are types of greedy algorithms. Orthogonal greedy algorithm basically identifies the indices of the support of sparse vectors using the projection procedure. So here we define the orthogonal greedy algorithm. Let K be a Hilbert space, and K is Hilbert space. R naught is any vector in Hilbert space, and then we set G naught of f is equals to 0. Therefore, each n greater than 0, we inductively choose fn plus 1 in Hilbert space K, such that the absolute value of inner product Rn fn is equals to supremum of I of absolute value of inner product Rn with fi, and this step is called the greedy steps, and we assuming that this supremum is existence. Then we define the G node fn plus 1. This is the nothing but orthogonal projection of f on the subspace spanned by the f1, f2, fn plus 1. Then we define R node n plus 1. This is nothing but f minus G node n plus 1 f. And this algorithm stop when either R node plus 1 is 0 or R node Rn plus 1 is less than epsilon, where epsilon is some pre-assigned value. So here we recall the definition of frame. Here also K is a Hilbert space. Then the sequence Fs is called the frame for K if there exists two constant A and B such that A norm of H square is less than equals to absolute value of inner product F with Fs square, which is less than equals to B norm of H square for all, H in Hilbert space K. The scalars A and B are called lower and upper bounds for the frames respectively, and these frame bounds are not unique. If they are equal, then we say that this frame is tight frame, and when these are equals to 1, then we say that this frame is Parseval frames. Tikhonov regularization aims to find a valuable approximation by the transforming the original minimization problem into a penalized least square problem, which allow to incorporation of a penalty term to guide the optimization program. So we have Ax, we transform the system Ax equals to f into this equation 3. Now we have to motivate to find x in Cn such that this minimize this problem. Minimum of x in Cn such that norm of Ax minus f square plus lambda Lx square, where lambda is a regularization matrix of order n cross n, and L is a regularization matrix of order n cross n, and lambda is a regularization parameter. The penalized least square problem is standard form if L is identity matrix, and in general form otherwise. The regularization parameter lambda control the weight given to the regularization term relative to minimization of residual term. The above equation can be written as the minimum of A tilde x minus norm minus f, where A tilde is nothing but the concatenation of two matrices A and square root of lambda L, and the f tilde is nothing but the concatenation of two column vector f and 0. So we may write the normal form of above equation as a tilde star a tilde x, which is equals to a tilde star f tilde. If kernel of a with if kernel of a is disjoint with the kernel of L, then the Tikhonov minimization problem has a optimal solution, which is x lambda, defined as x lambda is inverse of a star a plus lambda L star L into a star f. The main challenge is the choose a suitable value for the regularization parameter lambda. We will assume that we have a known bound for the norm of the noise vector n, and to determine the value of lambda, we can employ the discrepancy principle given in the paper written by the Fourier and Rizal, a new Tikhonov regularization method. And however, using the discrepancy principle to find a lambda usually involves solving the problem 3 multiple times with the different value of lambda. In our analysis, we consider the problem of restoration of the signal x in L2ZD. L2ZD is nothing but the complex values CD from the noise data and the noise signal G in L2ZL using the frame matrix B of L2ZL. And here B frame matrix means a finite matrix which is a full rank. Using the frame matrix B of L2Z as a measurement matrix, to do that, we solve the following linear equations: Bx equals to G, and G is corrupted by noise. So we can write this is as G diamond plus N, where G diamond is error-free vector. Instead of solving equation above, we use Tikhonov regularization to solve the minimization problem for n sparse vector. N sparse means a vector has at most n non-zero entries. So we solve the minimization problem of n sparse solution xt, which is the argument minimum of x in L2ZD, norm of bx minus g square plus lambda norm of x square, such that the xt is n sparse vector. So solving 6 is equivalent to the solving the conventional least square problem. Xt is argument minimum of norm of b tilde x minus g tilde, such that the sparsity of xt is at most n. So where g tilde is nothing but concatenation of two column vectors g and 0. Similarly, b tilde is the concatenation of matrix B and the square root of lambda and identity matrix. So in the conventional orthogonal gradient algorithm, the least square problem is the core tool of the algorithm, where we find x omega in L2 z omega that minimize the problem, the norm of b omega x omega minus g. In order to obtain the efficient recovery from noise model, we modify the conventional orthogonal by employing Tikhonov regularization to approximate the unknown solution. In fact, we find x omega in L2 z omega that minimize b tilde x omega minus z tilde. Basically, we replace b omega by b omega tilde and g replaced by g tilde. Subsequently, we change the other component of orthogonal gradient algorithm, and we term the new algorithm as Tikhonov orthogonal gradient algorithm. So before define the Tikhonov gradient algorithm, first we define peak matrix, and peak matrix is let omega be a subset of a natural number, and then the peak matrix is defined as u omega. U omega is the matrix EKI, EK1, EK2, EKN, and EKP, where EKIs are the standard EKIs are element in standard orthogonal basis in L2 ZD. And similarly, we define the lift matrix. Lift matrix is nothing but transpose of shift matrix. So this is the Tikhonov orthogonal gradient algorithm, or T orthogonal gradient algorithm. So our aim is to approximate the solution, minimize x such that x satisfies this inequality bx equals to g. So we have input b and g. Initializing case, we set x naught equals to 0, r naught equals to g tilde, and omega naught equals to phi. And for k greater than k equals to 1 to up to n, we inductively choose I k in d. The square d is nothing but the element in natural number from 1 to up to d. Here d is a natural number, so square d is nothing but a subset of natural number from 1 to d. So ik in d square d such that the absolute value of inner product of rki minus f tilde ik is the supremum of absolute of inner product of rk minus f tilde fr tilde. Then we update omega k. This is nothing but omega k minus 1 and union ik, and the take b omega tilde is b tilde and u omega, where u is a pick matrix, shift matrix. Then define xk as argument minimum of z omega k such that argument minimum of g tilde minus b tilde omega k z omega k over z omega k for z omega k in L2 z omega k. Then we update rk as g tilde minus b tilde omega L and the xk. Then output, if algorithm stops at fifth iteration, then the output is x bar is u omega p xp. In the above algorithm, if we see that b tilde omega k xk is nothing but the orthogonal projection of the element chosen by first k iteration, orthogonal projection of g in g tilde on the subspace spanned by the element choose up to first k iterations, where p omega k is a orthogonal projection of g tilde on the span fi, where I is omega k. Moreover, p omega k can be explicitly written as p omega k b tilde omega k b tilde omega k plus, where b tilde omega plus 1 is the pseudo inverse of b tilde omega k. Thus we have x k is nothing, x k is b tilde omega k plus g tilde. Also the residual vector can be written explicitly as r k is g tilde minus b tilde omega k x k, which is nothing but g tilde minus orthogonal projection of g on the space span by fi I in omega k, and this is nothing but the complement of orthogonal projection of on g on omega k. So if omega is subset of d, then we define the match matrix as m omega. This is the p omega per b tilde. So we can write as m omega as b tilde d omega plus b tilde omega complement d omega complement minus p omega b tilde omega d omega minus p omega b omega complement tilde d omega. So here p omega b tilde d omega cancel out with b omega d omega, because the b omega is nothing but the orthogonal projection span by the entry chosen in omega. So b tilde omega d omega is cancelled by b omega b tilde d omega. So that here remaining terms are b tilde omega complement d omega complement minus p omega b tilde omega complement d omega complement. So this is nothing but p omega per b tilde omega complement and d omega. So it is clear that column vector of m omega indexing in the set omega is R0, because this is the orthogonal projection on that set. So now we can write the residual vector in term of m omega k as rk. This is the p omega k per g tilde. This is also equals to p omega k per, because g is nothing but b tilde x. So this is p omega k per g b tilde x, and so this p omega k per b tilde is nothing but match matrix m omega. So this is equals to m omega k x. So next we define the match vectors of TOG as HK. This is nothing but B tilde star RK. And note that HK in L2Z. And further we define this term. So first we recall the definition of restricted isometry property, and F or B frame for L2Zn. Then we say that this frame satisfies the RIP of order n if there exists a tau in 0, 1 such that for any x which is n square satisfying the inequality 8. And the inequality can be written as the modulus of bx, norm of bx square minus norm of x square. This is the less than equals to tau norm of x square for all n sparse vector x. And if lambda is subset of a natural number of sets 1 up to d, that such that the cardinality of lambda is less than n, then for every z in L to omega, we have a norm of b star omega, b omega minus I omega. This is equals to the supremum of z in L omega, b star omega, b omega minus I omega z inner product with z, and this is the less than tau, because b star omega, b omega minus identity is the positive definite of operators. So we define the norm of b star I, bi minus I in this way. The next lemma tells that if the frame matrix B for L to Z, ZL satisfy the RIP of order n with isometric constant tau, then the matrix B tilde satisfy the RIP of order tau plus lambda. And if X is L to Z is such that the X is n sparse, then since B, and we are assuming that B satisfy the RIP of order n, then we have the matrix B tilde is nothing but concatenation of matrix B and the root lambda and identity matrix. So norm of B tilde x square is nothing but norm of bx square plus lambda norm of x square, and B is satisfied the RIP of order n. So norm of bx square is less than equals to 1 plus tau norm of x square. So this is the less than 1 plus lambda plus tau x square. Similarly, we can prove the lower inequality. And from the last inequality, the norm of B tilde, norm of B lambda star B lambda minus I lambda, we can prove this the following lemma. This if UV in L2 ZD and lambda is the support of U union support of V, suppose that frame matrix B for L2 Z satisfies the RIP of cardinality of lambda with restricted isometric constant tau, then the modulus of inner product B tilde U with B tilde V minus inner product of U with V is less than equals to lambda plus tau norm of U norm of V. And we observe that the inner product of B tilde U, B tilde V minus inner product of U plus V is nothing but the inner product of B tilde U V, because the support of U and support of U and support of V is contained in lambda. So U and V we can write as, we can written as B tilde lambda U lambda in inner product with B lambda B lambda tilde with V lambda. Similarly, inner product of U we can write as U lambda inner product with V lambda. And if we take adjoint and the take B tilde lambda, then left side, then this is equals to the inner product of B lambda tilde star B lambda minus I U lambda and V lambda. So by Cauchy-Schwarz inequality, this is the norm of B lambda tilde star B lambda tilde minus identity norm of U tilde and norm of V tilde. And norm of U tilde is nothing but norm of U, because the support of U contained in the lambda. So we got this inequality. The following lemma states that if a frame matrix B satisfies the RIP condition, then the match matrix also satisfies the RIP with modify RIP constant. Suppose that frame matrix B for L2 Z satisfy the RIP of order n with RIP constant tau, and let omega is subset of D. Then if cardinality of omega is less than n, then we obtain the following inequality. And this inequality holds for every x in L2 ZD such that the x is n minus omega sparse, and such that the support of x with disjoint with omega. Moreover, m omega star m omega theta minus I, the norm of this matrix is less than equals to lambda plus tau upon 1 minus lambda plus tau. And this norm is hold for every theta in D every theta subset of D such that the norm of theta is less than equals to such that cardinality of theta is less than n minus cardinality of omega, and theta and omega are disjoints. The next lemma shows that if omega is subset of D and suppose that x cap in L to Z D such that the support of x cap is disjoint with omega, then we define H as match matrix M omega star M omega x cap. If the frame matrix B for L to Z L satisfy the RIP of order x naught 0 plus cardinality of omega plus 1 with isometric constant tau, then the absolute value of hj minus x tilde x cap j is less than equals to tau plus lambda upon 1 minus tau plus lambda norm of square norm of x cap, and this is hold for every j except j in omega. And then in the next result, we develop a sufficient condition for the identification step of the TOG. If omega subset of D and support x cap in L to ZD with support of x is disjoint with omega, then we define H as H equals to M omega star M omega x cap, and let the frame matrix B for L to ZL satisfy the RIP of order x cap 0 plus cardinality of omega plus 1 with restricted isometric constant tau. If the infinity norm of x cap is greater than 2 times tau plus lambda upon 1 minus tau plus lambda into the square norm of x cap, then the argument maximum of xi belongs to support of x cap. And this is our main result. And suppose that the frame matrix B for L to ZL satisfy the RIP of order n plus 1 with the restrict isometric constant tau, such that tau plus lambda is 1 upon 3 square root n, then any x in L to ZD with sparsity of x is less than n, then TOGA will recover x exactly from Bx equals to G in at most n iterations. And these are some selective references. Thank you.
Thanks, Professor Deep, for your talk. Is there any question for the speaker? Any comments? No? Well, thanks, Professor, for your presentation.
Thank you, sir. Thank you. Thank you.
So we are going to continue if there is no any comments. We have the next speaker is Usha with the presentation of democratic frames in Hilbert space. I don't know if he's already there.
Yes, sir, I'm ready. Yes.
Oh, perfect. So you can share your screen, please.
Okay.
And
Okay.
we wait for a moment. Perfect. We can see you, your presentation. So
Shall I start?
yes, please go ahead if you are
Okay.
ready.
Okay. Good evening to all of you. Myself Usha, and topic of my today's presentation is democratic frames in Hilbert spaces. And here is the outline of my today's presentation: introduction, preliminary, risk basis and greedy approximation, frames and greedy approximation, and references. So basically, to enhance data processing capabilities for large data sets, studying nonlinear sparse representation is crucial for tasks like compression and denoising. Sparse representations serve as a powerful analytic tools, finding application in image signal processing and numerical computation. M-term approximation involving a system of function is the key role to finding sparse representation. So in this particular direction, Temloke introduced the notion of greedy algorithm and greedy approximation in 1990s. And in the similar direction, S.J. Dilworth, N.J. Kelton, and many other researchers gave various necessary and sufficient conditions for Schroeder basis to be quasi-greedy, almost greedy, and greedy basis. And also recent findings highlight that greedy type algorithms are effective for nonlinear approximation in both M-term approximation with respect to basis and redundant systems. And if we are talking about the redundant systems, frame is one of them. Frames are fundamental for signal compression, storage, and transmission due to their redundancy, allowing elements to be represented in various ways. And Geber, Schaeffer, and Affin contributed to the development of frame in signal processing. And many researchers try to extend the concept of the greedy algorithm and greedy type basis to frames such as Professor Shubh Kumar Kaushik and Khol Timothy in the paper titled Frames and Nonlinear Approximation in Hilbert Spaces. So I start with the definition of the frames in Hilbert space. Let H be a separable Hilbert space with the inner product. A sequence Xn is called frame for Hilbert space H if there exist positive constants A and B such that the inequality 1 holds. The constant A and B in 1 are called the lower and upper frame bounds of the frame respectively. They are not necessarily be unique. If A and B are equal, then the frame is called A-type frame. And if A equal to B equal to 1, then the frame is called the Parseval frame. Next is the some operator. First one is the synthesis operator, which is defined from the L2 to Hilbert space H, which take a sequence in L2 to a series CK, XK, where K from 1 to infinity. And next one is the adjoint operator, which take a element of Hilbert space H to a sequence in a product X, XK for all X belong to Hilbert space H. And with the help of these two operators, we define frame operator from Hilbert space H to H, and which give the representation of an element of a Hilbert space H in term of the frame XK for all element X from Hilbert space H. Now the next definition about the different type of linear independence. So basically a sequence be let xk be a sequence in a Hilbert space H, then we say that it is linearly independent if every finite subset of xk is linearly independent, and we say that the sequence xk is W independent if whenever the series ck xk where k from 0 to infinity is convergent and equal to 0 for some scalar coefficient ck's, then necessarily ck equal to 0 for all k belong to natural set n. And we say that sequence xk is minimal if xj does not belong to the closure of span of xk's where k not equal to j for all j belong to natural set n. Here are the some basic notation which will be I will be used throughout this presentation. Summation n and tilde summation n are the set of all linear combination of length n of element xn with the specific type of coefficient, and sigma n and tilde sigma n are the best n term approximation and almost best n term approximation. And the last one is the n greedy approximant of for a frame. Let rho be a permutation of natural number such that we can arrange the frame coefficient in a decreasing sequence, and then we define the greedy algorithm for frames in terms of Gn. Here are the definition of the greedy frame and greedy type frames. So basically first one is the quasi-greedy. A frame is said to be quasi-greedy if there exists a constant C such that the inequality 2 holds for all X belong to Hilbert space H. Next one is the almost greedy frame. A frame is said to be almost greedy if there exists a constant C such that the inequality 3 hold for all of the X belong to H. And the next is greedy frame. A frame is said to be greedy if there exists a constant C such that the inequality 4 hold for all of the X belong to H. And here is the definition of the unconditional frame. A frame is called unconditional if there exists a constant k such that for all x belong to H and finite subset B of natural set, we have the inequality 5, where PB is basically the projection mapping. Last one is the democratic frame. A frame is called democratic if there exists constant D such that for any finite subset PQ of natural set N with equal cardinality, we have the inequality 6. The smallest such constant D will be called the democratic constant of the frame. Ridge basis and the greedy approximation. Lemma 1 is used to prove the theorem 2, which state that let xk be a frame for Hilbert space H and sigma be a finite subset of natural set N, and P sigma be the orthogonal projection from H onto H sigma, where H sigma is basically the closure of the span of xk's, where k belong to sigma. Then for all x belong to H, we have best and term approximation equal to infimum of norm of x minus p sigma x, where sigma is a subset of natural set and the cardinality of sigma is n. Next is the theorem 2, which says that every Ridge basis for Hilbert space H with bound A and B is greedy with a greedy constant square root b by a, and by the definition of the greedy basis, every greedy basis is almost and every almost greedy is quasi-greedy. So we can say basically that every Ridge basis for Hilbert spaces is greedy, almost greedy and quasi-greedy. Next is the frame and the greedy approximation. Lemma 3 is used to prove the theorem 4, and which state that let xk be a frame for Hilbert space H with bound A and B, and let sigma be a subset of natural set N, then norm of S sigma x is less than equal to B time of norm of x for all x belong to Hilbert space H. And theorem 4 state that every frame in Hilbert space H with bound A and B is quasi-greedy with the constant B by A. And theorem 5 state that every frame in a Hilbert space with bound A and B is almost greedy with the constant square root B by A. So in previous slide, we see that every Ridge basis is greedy, almost greedy, and quasi-greedy. And similarly, on the same pattern, every frame in Hilbert space is quasi-greedy and almost greedy. But by example 6, we try to show that not every frame in Hilbert space is democratic. So here we take the Hilbert space R4 and frame and the set xk's, where x1 equal to e1, x2 equal to minus e1, x3 equal to e2, x4 equal to e3, and x5 equal to e4. And there is a result that in a finite Hilbert space, a set is a frame if and only if it spans the whole of the space. So clearly xk's constitute the frame for the R4. Let P and Q be the set of the indices and with the cardinality 2, which so by 7 and 8, equality 7 and 8, equation 7 and 8, we can say that there does not exist any positive D such that the equation 8 less than equal to D time of equation 7. So by this example, we shows that not every frame in Hilbert space is democratic. And in theorem 7, we try to give the sufficient condition for frame to be democratic in Hilbert spaces. So let Xn be a linearly independent frame for H with bounds A and B. Then frame is democratic with the democratic constant square root B by A. Or here the bibliography. Thank you.
Thanks, Professor Usha. So,
thank you, sir.
Is there any question, any comment? No? Well, thanks for your nice presentation. So we
Thank
are
you so
going
much,
to
sir.
continue. Thanks. So let's see. The next speaker is Professor Amit Kumar. Are you ready?
Yes, sir. I'm ready.
Perfect. So, can you share your screen, please?
Yes, sir.
Okay.
Namaste, everyone. Today, title of my presentation is some numerical radius inequalities using maximization. This presentation is based on an paper with same title and communicated paper with the same title. We have done this work under co-supervision of Professor C. Kumar Kosik and Dr. Kole Timothy Bomai. I will start with some basic definitions which will be used throughout our presentation. First of all, numerical radius of a matrix. Suppose A be n square matrix of order n cross n. Then numerical radius of matrix A is denoted by will be denoted by omega, and it is defined as the supremum of mode of X transpose AX, where X belongs to Cn and norm of X is 1. Means X varies on the unit circle of Cn. And another term which will be used throughout our presentation will be unitarily invariant norm. A norm on Mn cross Nc is termed as unitarily invariant norm if norm of Au is equal to norm of UAV, where matrices U and V are unitary are any n cross n unitary matrices. Any unitary invariant norm of a matrix depends only on its singular values. So for any matrix, if we know its singular value, we can say we can tell what is its unitarily invariant norm. Introduction. Recently, Bhatia and Jain characterized operators whose numerical radius is bounded by 1. In this paper, we utilize its generalized version to establish various known and new numerical radius inequalities via optimization of matrix functions on the set of n cross n complex matrices with a numerical radius bounded by 1. Motivation behind our work is given the measures omega A and norm A. Here norm A you denote any unitarily unit norm on set of matrices, set of n cross n complex matrices. Given the measures omega A and norm of AU regarding the size of A, we can pose the following questions. For a given matrix B belong to Mn cross Nc, what are the smallest positive constants L1 and L2 such that the inequalities A and B hold? Here AOB, O denotes Hadamard product of matrices. Means if you are given two matrices A and B of same order, then AOB is just element-wise multiplication of the matrices. So our first problem is to find smallest L1 such that norm of AOB is less than equal to L1 norm of A, and second is norm of AU is less than equal to L2 time omega A. These two problems have attracted a lot of researchers. The second problem has been fully addressed, while finding a comprehensive solution to the first problem appears challenging. Progress has been made for some specific choices of B. For example, if B is a positive semi-definite matrix, then L1 comes out to be the maximum among diagonal entries of matrix B. Our objective in this article is to find the smallest positive constants Ki satisfying the following inequalities. Norm of ABU is less than equal to K1 omega A. Second, real part of A here means that A plus A star upon 2. Uh, and and similarly problem 3 and 4. Here problems 1, 2 and 3 are motivated by problem B, and fourth problem is motivated by problem A, which we have mentioned above. We will tackle these problems by maximizing the expression present on the left side of these inequalities over the set of n cross n matrices with numerical radius bounded by 1. Our contribution. Problems 2 and 3 are completely resolved in our analysis. Our solution to problem 3 allows us to extend an inequality by kidney from operator norm to class of all unitarily invariant norms. Even though we couldn't find definitive answers to questions 1 and 4, we derived effective bounds for K1 and K4. Leveraging our results for problem 1, we derived Johnson and Lee's solution for problem B as a corollary, along with some additional findings. This is the characterization given by Bhatia and Tanvi for all matrices whose numerical radius is bounded by 1. It was given by Bhatia and Tanvi, and this is our generalized version which we will be using. So this generalization says that numerical radius of a matrix A is less than equal to R if and only if A can be factored as 2R x star y, where x and y are n cross n matrices such that x star x plus y star y is In. Here In denotes the n cross n identity matrix. The first problem we have, as we mentioned above, problem 1. In that regard, we give this theorem. And for any matrix A belong to Mn cross n C and unitarily invariant norm U, maximum of norm of AB such that numerical radius of B is less than equal to 1 is less than equal to 2 times maximum of this. I mean, we get an function on Rn and bound in terms of an function on Rn. As an corollary, we obtain the solution which have also been found by other authors, which we have mentioned above, and as a corollary. And this is that corollary. This says that there exists a matrix A naught belong to Mn cross Nc with numerical radius 1, such that maximum of norm of AU such that numerical radius of A less than or equal to 1 is norm of A naught U. Here, the beauty of this result is that this matrix A naught is independent of the unitarily invariant norm you are choosing. So further on, we will prove that we have found parallel results for other type of functions of matrices also. Here, the function is norm of AU. In other cases, there will be another functions, and again, we will obtain matrices independent of unitarily invariant norm, and this maximum that matrix will work for all unitarily invariant norms. The construction of matrix A naught is proposed here. Again, most important thing about A naught is, as I told, that unitarily invariant norm of a matrix depends only on its singular values. So here I mentioned singular values of matrix A naught. The singular values of matrix A naught are 0, 1, and 2 with multiplicities m, 2n minus m, and m respectively. Here m denotes the greatest integer function of n upon 2. Next corollary of theorem 1 we obtain is maximum of mode of trace of AB where numerical radius of B is less than or equal to 1 is it will depend on whether n is even or odd. We will get to different results. And I have also proved that if A is a normal matrix, then maximum of mode of trace of AB, so the numerical radius of B is less than or equal to 1, is summation sigma IA, I is equal to 1 to n. Here sigma I denotes singular values of matrix A. So we can see that bound obtained in case of a normal matrix is much smaller than bounds obtained in general cases. So those bounds obtained, those are not that good. So there is some space for improvements. Sorry, sorry, there will be an inequality here in the general case, not equality. This is My mistake. Next result we obtained for any matrix A belong to Mn cross NC and normalized unitarily invariant norm. We have norm of AU is less than equal to n time omega A. So we have obtained here an uniform bound independent of unitarily invariant norm. And we have said that it will be n. Maximization of real part of a matrix on unitarily invariant norm of real part of a matrix on the matrix on the space of matrices with numerical radius bounded by 1. Here again we obtain that for any matrix A belong to Mn cross Nc and unitarily invariant norm U, norm of real part of A is less than equal to omega A into norm of In. So here the bound is obtained in terms of identity matrix. I mean, independent of what unitarily invariant norm you are choosing, here again bound is obtained in terms of identity matrix. So again, our obtained matrix identity matrix doesn't depend on unitary invariant norm. And because this theorem can also be proved similarly for imaginary part of matrix, so using both of them, we have obtained this corollary. We have also provided an upper bound for omega as well as a lower bound. Next, we have maximized this augmented matrix A star, unitarily invariant of this augmented matrix A and A star. It is an block matrix with first block A and second block A star. Again, we have obtained here that norm of A star, unitarily invariant norm of A star is less than equal to omega A time norm of A naught comma A naught star. Here, A naught is the matrix defined above in the corollary of theorem 1. So that matrix appears very much important to in our results. So again here again we are our result is independent of what unitarily invariant norm you are choosing. As in corollary of this theorem, we obtain an generalization for an inequality given by Kitney and celebrated inequality given by Kitney, which he had proved for only for operator norm on matrices. We have proved it for any class of unitarily invariant norms, and we have shown that it again this also depends on the matrix A naught. What bound you will obtain, that will be determined by matrix A naught. And again here A naught is the same matrix defined above. Our last problem we have considered in this work is maximization of unitarily invariant norm of Hadamard product of matrix A and B, where numerical radius of B is less than equal to 1. Again, our results depend on we obtain the bound in terms of norm of this diagonal matrix, and we obtain different results for the cases n is even or when n is odd. These are some of references we have used. Thank you.
All thanks, Professor Kumar, for your talk.
Thank you.
Is there any question? Any comments to Professor Kumar? No? Well, thanks again, Professor Kumar.
Thank you, sir.
So we are.
Can I stop sharing?
Yes, please.
Okay, thanks.
Perfect. So we are going to continue with our last speaker. I see is Professor Manuel Bernal. Are you ready there?
गंदी थी, बहुत गंदी प्रेजेंटेशन।
Mm-hmm. Mm-hmm. Okay. We are waiting to Manuel. Just for a moment.
Give me a moment, please. Give me a moment, please.
Okay, okay, no, no hurry.
Can you see my windows?
No.
One moment, please. Can you see my windows?
No. Ah, perfect. Now, yes. So we are we're going to continue with Professor Manuel Bernal, who is our last speaker. He is from Mexico, and he's going to talk about the properties of the Fourier sign transform related to the integrability framework of the Hanston-Kurzweil integral. So, are you going to speak in English or Spanish?
I prefer Spanish.
Spanish.
Or
Español.
English.
Okay, en español no hay problema. Tu presentación está en inglés, ¿verdad? Entonces ya con eso se hace más fácil. So, thank you to everybody to stand by. We are going to continue with our last speaker, and he's going to speak in Spanish, but the slides are in English. So, please, Manuel, adelante.
Okay.
Te cedo la palabra.
Gracias por su tiempo. Bueno, a lo largo del tiempo se ha estudiado la integrabilidad de la transformada de Fourier. La transformada de Fourier pues se puede dividir en la transformada seno y coseno. Bueno, a los profesores Alfredo, Javier y Juan Héctor Arredondo han trabajado en cuestiones de integración generalizada. Y en particular, pues yo trabajé con el profesor Juan Héctor, la doctora María Guadalupe, y en algunos comentarios me ha ayudado el profesor Javier Mendoza. Entonces, trabajamos la integrabilidad de la transformada seno. Ah, el contenido de esta plática es la introducción, la transformada de Fourier en un espacio no clásico, la integrabilidad de la transformada seno y las conclusiones. Esta es la definición de la transformada de Henson-Kurzweil, entonces es muy parecida a la integral de Riemann. La única diferencia es de que tiene una función medidora que me permite hacer, desde mi punto de vista, los intervalos más pequeños o más grandes, dependiendo de cómo oscila la función. Entonces, esta integral con esta pequeña modificación es más general que la integral de Riemann y la integral de Levet en ciertos aspectos, no en todos, pero sí en ciertos aspectos. Ah, los teoremas más importantes, hay muchos, pero los que más he utilizado en este desarrollo pues son el teorema de Hacke, el teorema del multiplicador, que es pieza angular para poder desarrollar la teoría de la transformada de Fourier en espacios no clásicos. Bueno, la transformada de Fourier en un espacio no clásico es esta. Cuando se tiene este resultado, prácticamente viene de un artículo que publicó la doctora Guadalupe Morales, el doctor Francisco Javier y el profesor Arredondo, y creo que también el profesor Escamilla, no recuerdo muy bien, pero pues es un resultado que viene en algunos aspectos acerca del teorema de Riemann-Levet para funciones de variación acotada. Y bueno, se introduce un nuevo espacio, que es la suma de este espacio vectorial, que es la suma de dos funciones, una función en el espacio L1 y otra función en el espacio L0, donde pues cada una pertenece a estos conjuntos. La transformada de Fourier se puede definir de esta manera, está bien definida. Si uno hace que esta función F2 sea 0, pues prácticamente recuperamos la integral de Lebesgue. Bueno, la transformada de Fourier en el sentido clásico. Si hacemos F1 igual a 0, pues retomamos el teorema publicado por los profesores Arredondo, Morales y Mendoza. Bueno, básicamente eso es lo que... Estas integrales son en el sentido de Henson-Kurzweil. La integrabilidad de la transformada seno. Bueno, para poder abordar la integrabilidad transformada a seno, hay una cuestión que demostró a Alfredo, el profesor Mendoza y el profesor Arredondo, que la transformada coseno es un operador lineal acotado, mientras que la transformada seno tiene una propiedades cualitativas diferentes a la transformada coseno. Entonces, pues nosotros damos la condición necesaria y suficiente, necesaria para que la integral, la transformada seno sea integrable, ya que no es un operador acotado, parece ser. Bueno, habría que estudiar un poquito más ese tipo de cuestiones. Bueno, se dan estas dos funciones, donde esta función no pertenece a las funciones de Lebesgue integrables y esta otra función no pertenece a las funciones Lebesgue integrables, y cuando uno busca su transformada, pues no es Henson-Kurzweil integrable. Bueno, esta función definida de esta manera no es de variación acotada, y cuando uno realiza un cambio de variable y hace las operaciones adecuadas, pues resulta que no es Lebesgue integrable, como me lo pide, como Give me a moment, please. There's my question.
Okay, now, however, we have some technical problems. We wait for Manuel for just a moment. There is always technical problems in this online seminar, so please stand by.
My internet is slow. I'm sorry.
Oh, we have some problems with the internet signal. We can wait just for a while, no problem.
Can you see my windows?
Not yet. No. Intenta otra vez. A lo mejor hay un retraso. Se ve todo negro.
Not yet?
No. Oh,
Give me a moment, please.
we continue with technical problems, so please wait just for a few moments. Okay, perfect. Ahora sí se ve. We can see the presentation now, so we are going to continue with Manuel's presentations from Mexico. So please, Manuel, continue. Adelante.
Okay.
Creo que era la siguiente hoja. Sí, esa, en esa estabas.
By computed
Perfect.
integral. A computed integral is no converse. We had that the f over x no belongs Lebesgue integral. Furthermore, Alfredo and Arredondo shown that the limits diverse, thus by the Hackettarian relation free half. We define the function. The graphic of the function is as follows: step the crescent function, a typical function in the theory. Now let's solve the computed its integral into this integral diverges. Thus f2 over f is non-Lebesgue integral. Applying the corollary, see below, we have the Fourier sines transform of f2 in Henson curve integral in this interval. If and only if the limit exists, then by the theorem of the Henson curve integral, with that is its integral exists, but now we analyze the divergence of the line, the limit for the integral, applying the chain of variable. We have the result. By properties the same, we have that. Let's also consider the mathematical objects by the dominant convergence theorem. We have that the limit is classic. If this the same variable, then the function f2 is a constant on the interval. We have the following. Let's solve the considered this is object mathematics by the dominant convergence theorem. Thus we have time using the properties of the limited super and limited infinite one get. Component this beginning the function, a positive monotonic decreasing function on the real from the reference we have time the next result it's following that that is positive, removing night in the expression age. Yet from the theorem 6.93, we obtain the following consequence. Therefore, the limit is diverse. The main theorem is following. Let B be a real function in BB0 so that f over f in L1 dance Fourier sine transform in HK. Es Henson curval integral. The next corollary is a consequence of the main theorem. Conclusion: this is example indicate that the conjunction f over x in L1 is essential to ensure the HK interval of the Fourier sine transform when f is the bounded variation function. By reference, thank you.
Thanks to Professor Manuel for your talk, for your effort. So is there any question, any comments for the speaker?
Hello, Professor.
Go ahead.
Yeah, actually, I was waiting for this presentation. Might be his network issue was there. Can you please share the presentation? I have given my mail in the chat box.
Ok. Sí, Manuel, están diciendo que sí.
Check in the chat, please.
Ajá, te mando el correo para que compartas la presentación. Y también en la mañana hubo unos con problemas técnicos. Entonces sí es sí es el detalle de estos seminarios, ¿no? Ok. Professor Bernal is going to share the slides by mail because there is some technical problems here. But is there any question, any comment?
No, I will read, then if question come, then we'll discuss. Thank you.
Okay. Someone else? If you see the chat, you will find the link for YouTube in order to see the seminar complete. So I don't know if someone else want to share something. Professor Nikhil, any comments? Professor Mendoza, Professor Arredondo.
No comments.
No comments.
Please, Professor Nikhil, can you close the seminar? And would you like to announce something? What is gone? What is, please?
Thank you all for attending the presentations and be part of this international conference. And as we have discussed on the very first day, that is the 4th editions, and we are just looking forward for further editions to continue. And I still remember that in 2019 when Professor Juan visited us and we started thinking over this idea of joint seminars with Mexican mathematicians and Indian mathematicians. That was, I mean, a very good idea, which we discussed together. And now, I mean, now a lot of people from various countries are joining. And this time, Dr. Anirudh from China, Professor Askari Himmat from Iran, many Mexican participants, many from India. So it was a very enriching experience in terms of research also. And last but not the least, as you all must be aware that after this conference, we are going to announce one special issue, which will be published in Poincare Journal of Analysis and Application, which is a Scopus indexed journals, which is also indexed under MathSciNet and ZB Math. So hopefully you will receive an email to submit your research work. Obviously, that should not be published elsewhere. And then you can submit those papers and they will get reviewed. And hopefully we will get a good special issue for this conference. Thank you very much. And now I think Professor Juan would like to say something and add few things to what I have already said.
Not really. I wish only to thank everyone, and we hope to be able to continue this seminar in the future with your contribution. It will be surely successfully as it was in this occasion.
Yeah. Thank you very much. Maybe if Professor Xavier can add few words.
Professor Mendoza has told me by phone that he has problem with his internet connection, so he's not able to
I think
to say something.
Okay.
So
yeah, I think that
there is always problems with.
I think now we can
network.
ask some of the participants to just share their thoughts regarding their experiences, and one by one, if they are willing, they can just open their mic, and then it will be nice if they can also open their video cameras so that we can all see their faces and can listen to them clearly. Thank you. I think Dr. Sumit is available. He can share his experience regarding the conference.
It is definitely a nice experience to join via online media. I know this conference is going via hybrid mode. Lots of Mexicans are also there offline, and we are also here online. So it's really a nice experience to connect you with all. Definitely, it's a good way to communicate the research that is going on all around the world. And not only while showing our research work, we can also think for communicating our research from different parts of the world, and that actually would be a more better idea. And I will be looking forward to see you all again in this conference, 5th edition next year. All the best for the organizers, and I'm really happy to be the part of this. Thank you very much.
Thank you very much. Yeah. Maybe if Professor Khole Timothy can share some of his thoughts. I think he is available online. Professor Timothy, are you able to hear us? Can you please share your experience regarding the conference?
Yes.
Yeah.
Thank you, Nick, for the opportunity. I think this is a very good experience for all of us, and especially interacting with people from different countries, especially the mathematician. We come together, and I hope that we can meet offline one day, not only online, and we can interact each other, and then apart from research, we can also meet each other. We can have fun, and then we can meet each other, and then lastly, like I learned many things because many research scholars come and share many new things, and this is a beginning from my side.
Yeah.
And I always look forward that we'll meet each other one day for sure offline, whether
Yes.
in India or in Mexico.
Yes.
Thank you.
Yes,
Nice
of
to
course.
hear from you. Thank
Or
you
in
very much.
Oman.
Please, Carolina, may
Professor
we
Manika,
want to hear you.
yeah, yes.
Hi everyone. Hi Professor Juan. Oh, it's nice to see all of you. For me, it was a great pleasure to participate 1 year more of this conference and see all of you, to learn from you. Oh, I just thank for this experience, which was very nice. And I hope to see all of you in person one day, no? Thanks, many thanks.
Thank you.
Thank you.
Of course, it will be very nice to meet you.
Oh, likewise, it's the same.
Okay, well, and then
Thanks for the opportunity, Professor Juan, and for everything. It was very nice to meet all of you again.
thank you. Professor Milam, do you want to comment something?
Everything was already said. I thank very much to organizers of this meeting. It was a very, very nice and a very good experience. And much better it would be if we were all in Mexico and
yes,
enjoying.
I think
sea.
so, Professor. We hope that in the near future we can organize something and
or maybe in India, Professor Juan.
No,
and now we have another place, Oman also. Maybe you will love this place to visit and to share your research experience.
well, I would say that Mexico and India is more or less the same, because in India I feel like at home, and Mexico has also this we are also very hospital.
Yeah,
I know.
Like in India.
Yeah, we have a lot of similarities. Yes.
Someone does someone want to share?
Maybe Dr. Kalita is here. Maybe he would like to share some of his experience. Dr. Kalita, how are you?
Yeah, I'm very fine. Thank you. I like to congratulate you and Professor Francisco and other organizer. It was nice. I am organizing with this since second session. Of course, I was missing the first. I am with you and I enjoyed. And this time, many new faces I have seen. I have seen our network is growing. So hopefully, I also eagerly waiting to meet you all physically.
Yes.
And we should try. Thank you very much for giving
for sure. You're most
such a nice platform to youngsters also who are coming the research newly. And they are doing very good from India as well as Mexico, Iran. Also, I have seen yesterday, it was very good. Actually, Middle East also covering.
Yes.
Yeah, I can understand your effort.
Yeah.
Thank you very much.
I think Professor Mendoza is with us, and he can also share his, if his mic is working, maybe. Okay. If anyone is interested in saying few words regarding the conference, they are most welcome. And I think Professor Anu Kapoor, she joined this session for the first time. If she is here, she can also share her experience. Maybe I think she has now signed out.
Oh,
Yeah.
tengo que hablar, ¿verdad? No, thank you very much to all the participants in this event. This is very important for us. Thanks to Carol, to Professor Milan, to Emanta, to Professor Sumat Kumar, Nikhil, Alfredo, and all the participants. I am happy by these events. Thank you very much.
Okay, very good.
It's called.
Well, who is going to begin to say goodbye? Nobody wants to say that.
Maybe we can
That is
start one more
that is
session.
good for that is good. That it means that the event was. I hope you were comfortable, and we hope that the next time we can organize better, always better, and so that we can make why not a future joint work. I am always trying to see what other people make or do, and that is an advice for young people. Maybe at least you will learn more if you see what other people do. Well, I say thank you, all of you.
Thank you.
Thank you very much.
Okay, so maybe I'm the oldest one, so I can say goodbye to everybody and close it. So
yes.
bye
Thank you
bye.
very
Goodbye,
much,
Milan.
Professor Milan.
Thank
Goodbye.
you.
Thank you, Professor Javier. Thank
Thank
you,
you, Carol.
everyone. It was very nice to meet you again. Thank you.
It's a
Bye.
pity that I haven't seen Lupita, though she is not far from Prague.
Yes. Okay.
So, bye bye.
Bye bye. Bye,
Goodbye
Professor.
to everybody.
Bye, Professor Nikhil. Bye. Bye, Alfredo. Bye bye.
Bye, Professor Maria. Nice to see you.
Nice to see you.